Hello there and welcome back to the Sleep Science. Tonight we're gliding far, far beyond our little planetary bubble, out where sunlight thins to a whisper and space begins to feel like an endless waiting room. Our topic, the latest data from 3I/ATLAS, the third confirmed visitor from another star, and the quietly terrifying anomaly hidden inside that data. You probably won't survive this one, emotionally at least. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop your location and local time down in the comments. I love seeing this sleepy constellation of night owls light up across the planet. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You hover, weightless, somewhere between curiosity and awe. The black around you isn't empty, it's textured with radio whispers, streaked by data streams and pixel bursts from telescopes trained on a faint smear of light. The label stamped across the observation feed reads 3I/2025A1, Atlas, the third interstellar interloper ever confirmed. You watch the faint dot drift against background stars, a ghost of sunlight crossing millions of kilometers, and something in the pattern makes your spine itch. At first it looked ordinary, or at least ordinary for a rock from another star system. The Atlas survey in Hawaii picked it up late in 2025, a dim, fast-moving speck against a screen of static. Within hours, algorithms flagged its path as hyperbolic. It wasn't bound to the sun. Another outsider following in the icy trails of Oumuamua and Borisov, but when astronomers fed its numbers into orbital solvers, they blinked. The velocity vector wasn't just fast, it was wrong. Picture the solar system as a well-kept pond. Every comet or asteroid you've ever heard of ripples within it, tugged by gravity's patient fingers. Yet 3I/ATLAS sliced through those ripples like a skipping stone flung from somewhere far beyond, its incoming angle and eccentricity implying an origin no model could place. You can almost hear Newton muttering under his powdered wig, tapping quill against chalkboard, muttering, "That shouldn't happen." You zoom closer, or rather your imagination does, because of course no probe is anywhere near it. Through simulated imagery, the object looks small, maybe a few hundred meters across, but its reflection curve is peculiar. No coma, no tail, no photometric flutter from rotation. It gleams faintly, like polished basalt under a dying flashlight. Astronomers argued about albedo coefficients, while you sip cosmic coffee and think, maybe it just doesn't want to be understood. Historical footnote: our first true interstellar visitor, 1I/Oumuamua, entered headlines back in 2017. It tumbled end over end, sped up slightly as it left, and sparked the kind of speculation that fuels Reddit threads and late-night documentaries. 2 years later came 2I/Borisov, a textbook comet with a reassuringly messy tail. And now, this, 3I/ATLAS, the one that seems to have read the script but decided to improvise. The discovery logs read almost poetic in their precision. January 2025. Automated Atlas telescopes record an unusual streak. February. Confirmation from the Pan-STARRS array. March. Data relayed to the Minor Planet Center, which promptly classifies it as hyperbolic with excess velocity. April. Early spectra hint at volatile compounds that shouldn't survive the temperature profile it occupies. And by May, someone notices that its light curve oscillates at intervals suspiciously close to 26 hours, roughly the length of a day plus a cosmic wink. You drift through these data points like dust motes in a shaft of sunlight. A quiet joke forms in your head, something about aliens running on Earth Standard Time, but you let it pass. Humor, after all, is the last defense of a species confronted with the incomprehensible. Then comes the anomaly that starts the headlines. A faint gravitational discrepancy. When plotted against predictions, the object's position lags by fractions of an arcsecond. Tiny, yet consistent. Either the math is wrong, which would make Newton faint, or 3I/ATLAS carries more mass than its brightness suggests. Picture a hollow shell with a dense heart, or a structure made of materials unknown to terrestrial chemistry. Some late-night commentators call it a probe, others a natural oddity. Historians still argue whether ancient astronomers might have glimpsed similar visitors and folded them into mythic stories of wandering stars. You watch as the first press conference unfolds, scientists in crisp shirts, a wall of charts behind them, coffee cups just off camera. We're not claiming anything extraordinary, one insists, which of course guarantees that everyone hears the exact opposite. The live stream chat floods with alien emojis, and you imagine the object itself, silent, inscrutable, surfing the solar wind with a smirk. Somewhere in the background of all this data, there's a sound, not literal but perceptual, a slow pulse that reminds you of breath. Data packets arriving every few minutes, telemetry spikes that feel almost alive. You tell yourself it's coincidence, that cosmic noise just happens to find rhythm. Still, the human brain is wired for pattern, and pattern is what keeps you up at night. The ancient Egyptians once tracked a bright visitor they called Sekemka, the traveller who cuts the sky. Historians debate whether it was a comet, a nova, or poetic invention, but the description, metal bright, tailless, swift, could fit an interstellar object. Perhaps every few thousand years one of these outsiders slips by, leaving only stories and a faint scar of wonder. You scroll through the newest observation file. The numbers shimmer, right ascension, declination, magnitude, each a note in an invisible melody. Something in the metadata blinks, an unexplained calibration offset of 0.04 seconds. Not much, unless you know the precision astronomers crave. It's the cosmic equivalent of a heartbeat skipping a beat. The servers hum on, the object continues, and you, somewhere between sleep and starlight, find yourself whispering questions no dataset can answer. Because maybe the true anomaly isn't in the numbers at all. Maybe it's in how your chest tightens when you realise that, out of all the infinite space, this thing found its way here, past Jupiter's cold watch, across the thin blue veil of your homeworld's orbit, and on toward nothing. And it leaves behind just enough evidence to make you wonder if it noticed you looking. You drift backward through time, following the trail of our cosmic visitors like breadcrumbs scattered across centuries. Before 3I/ATLAS, there were only two, and even those felt like myths made of math. Oumuamua and Borisov, the first hints that the universe sometimes knocks politely before barging in. You picture yourself at a dark hillside observatory in 2017, a thermos of cooling tea beside you, eyes glued to the digital sky where a faint cigar-shaped blur begins to slide across the sensors. That was Oumuamua, the name borrowed from Hawaiian, meaning a messenger from afar arriving first. It came from beyond the sun's dominion, and for a brief month the world held its breath. The mainstream fact, Oumuamua's speed, about 87 kilometers per second, made it the first confirmed interstellar object ever observed within our solar system. Its brightness curve suggested it was 10 times longer than it was wide, spinning end over end every 8 hours. When it accelerated slightly on its way out, people smiled nervously. Comet jets could explain it, they said. Except there was no visible gas, no dusty halo, nothing but that bare, tumbling shard. Historians still argue whether the subsequent public fascination marked the moment space science slipped into pop mythology, or simply the human instinct to look for meaning in the void. Then came 2I/Borisov in 2019, a comet so ordinary it was almost comforting. A Ukrainian amateur astronomer, Gennady Borisov, found it through his homemade telescope. A regular guy spotted something from another star, reminding everyone that discovery isn't always corporate or cold. Borisov looked and said, "That one doesn't belong." And he was right. Its tail billowed just like comets born under our own sun. You could practically hear astronomers sigh with relief. Finally something that behaves. Between those two events, Oumuamua's sleek silence and Borisov's icy familiarity, humanity built an expectation of what interstellar visitors should be. You could draw a line between the two and imagine a spectrum, mysterious on one end, mundane on the other. Then, years later, 3I/ATLAS appeared and took a cosmic eraser to that neat little graph. But before we chase its anomaly further, you linger a bit with those earlier wanderers. You picture how it must feel for them, objects older than the sun itself, wandering through dark gulfs for eons until chance drags them into a warm, photogenic solar system filled with creatures who instantly demand to know their business. It's like walking into a small-town diner and having everyone stare. You'd want to speed up too. There's a quirky historical tidbit tucked in the archives. In 1991, long before Oumuamua, a strange radio signal called the WOW signal briefly puzzled SETI researchers. 72 seconds of unexplained intensity from the constellation Sagittarius. It never repeated. Some fringe theorists later connected that to the trajectory of Oumuamua, claiming that both came from the same region of space, as though the universe were clearing its throat decades before stepping into view. Scientists dismiss that, of course, but you can't help imagining it. Space making small talk before sending guests our way. You trace the pattern across decades of data. The solar system, it turns out, isn't a sealed garden. It's more like an airport terminal, objects constantly passing through, some just changing planes. The interstellar population might number in the trillions, drifting between stars like pollen. We've only spotted a few because our telescopes are toddlers, barely able to focus beyond the nursery walls. With projects like the Vera C. Rubin Observatory, we'll soon catch many more. Statistically speaking, 3I/ATLAS shouldn't be special. Yet here you are, still awake, thinking about it like it texted you first. Astronomers often describe these objects in the language of kinship. Visitors, travelers, messengers. You roll the words around in your mouth, liking how human they sound. Maybe naming things from the sky makes them less frightening. The Babylonians called comets hairy stars and thought they foretold kings' deaths. The Chinese catalogued them meticulously, assigning each a personality: the broom star, the long-tailed one, the returning guest. And when Oumuamua arrived, some Hawaiian elders gently reminded scientists that the word also implies a scout sent ahead. It wasn't a stretch to wonder, ahead of what? There's a certain softness in thinking the cosmos sends postcards rather than projectiles. Still, you know how the mind works. The moment something doesn't fit the model, we fill the gap with wonder, or fear. A 2020 paper suggested Oumuamua might have been a fragment of nitrogen ice from a shattered exoplanet, like a sliver of Pluto launched across eternity. Others countered that it was too reflective, too weirdly shaped, too clean. And then came Avi Loeb, the Harvard astrophysicist who said out loud what everyone else only whispered. Maybe it was artificial. Historians still argue whether that statement broke scientific decorum or simply reminded the world that science is, at its core, curiosity with better funding. Loeb doubled down, writing a book, giving interviews, suggesting that we just ignored our first alien technology, and you, lying here in the dark pretending to be relaxed, remember how thrilling that felt. A whisper of cosmic intrigue in the middle of a global news cycle otherwise obsessed with more terrestrial nonsense. When 3I/ATLAS showed up years later, that earlier tension returned, like déjà vu with a new twist. You scroll through headlines repeating the same cautious phrasing: unidentified behavior, unexpected trajectory, further analysis required, the scientific way of saying, we have no idea, but please don't panic. The Atlas system itself deserves a small bow in this story. It stands for Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes scanning the sky for anything on a collision course with Earth. Designed to protect us, it ended up detecting something utterly indifferent to us instead. There's irony in that, like setting a mousetrap and catching a ghost. A curious fringe group online calls 3I/ATLAS the third messenger, a phrase that sounds grander than their grainy memes deserve. But you smile anyway. Even the skeptics can't quite resist dressing science in myth's old robes. Maybe myth never left, it just learned how to use a data pipeline. As you drift towards sleep, numbers turn into stories. The orbits become characters, the trajectories conversations. You imagine Oumuamua and Borisov whispering to each other somewhere in deep space. How did they take it, asks one. They're still arguing, the other replies. And far away, 3I/ATLAS spins silently, carrying the punchline you haven't heard yet. A faint ping echoes from the observation feed. A signal routine and meaningless, yet your mind grabs it like a secret. The next line of code waits to be read, and you realize that what keeps you awake isn't the object itself, but the question it raises. Why did it come now? Maybe coincidence, maybe cosmic timing, or maybe, just maybe, the universe has a sense of humor too. You settle back into the hum of machines, an orchestra of servos, fans, and digital heartbeats. Every night, they watch. That's their entire existence, scanning, comparing, alerting. The Atlas telescopes are like sleepless eyes perched atop Hawaiian mountains, drinking starlight through lenses the size of your kitchen table, but backed by computing power that could make an ancient oracle weep. You imagine standing beside one in the cool pre-dawn air, hands in your pockets, watching it pivot gracefully towards some anonymous patch of sky. The stars shimmer above Mauna Loa, patient as old gods. The mainstream fact, ATLAS, short for Asteroid Terrestrial Impact Last Alert System, became fully operational in 2017 with a single, beautiful mission to spot killer rocks before they spotted us. Each of its twin telescopes scans the entire visible sky several times each night, sensitive enough to catch a faint object days before it might hit Earth. Over the years, it's expanded, adding nodes in Chile and South Africa, a network spanning hemispheres like a cosmic safety net. You can almost hear the system breathe, sweeping, clicking, logging, repeating, and then, one night in early 2025, that rhythm hiccuped. The story goes that the detection algorithm didn't even flag it at first. The object was small, faint, magnitude 19, and moving oddly slow for something interstellar. But by the second night, its motion refused to fit any predicted orbit. The automated software, normally quite smug about trajectories, began spitting out increasingly improbable solutions, retrograde paths, negative eccentricities, even one simulation that placed the object starting inside Jupiter's orbit. Someone on the night crew joked that the computer had developed a sense of humour. By morning, no one was laughing. You picture the scene: the control room washed in monitor glow, coffee cups orbiting keyboards, astronomers half whispering to each other so as not to disturb the data gods. Then the call goes out to Pan-STARRS, the veteran sky survey on Haleakala. Within 24 hours, confirmation. It's real, and it's not local. Another visitor has slipped through the sun's gravitational fence, but something about this one feels different. You glance at the light curve, brightness plotted over time, and it's eerily smooth. Even comets wobble as they spin, but 3I/ATLAS glides with the kind of steadiness that belongs more to machines than to rocks. You imagine the data scrolling past like an EKG, perfectly even, hypnotic. Someone mutters, "It's not tumbling." Another replies, "Then it's aligned." Fringe tidbit. One engineer later confessed that for a single frame, the telescope registered a faint linear artifact, like a glint, running parallel to the object's path. Cosmic ray? Probably. But the same anomaly appeared in a backup camera 3 milliseconds later. Statistically meaningless, officially ignored. Yet somewhere, a Reddit thread had already titled it "The Shining Rod of a TLAS." Historians still argue whether technology has killed or amplified the sense of wonder. In the old days, a strange light in the sky was enough to reshape empires. Now it becomes a spreadsheet cell, filed and forgotten, unless, of course, it refuses to behave. You watch the next few nights unfold in fast forward, additional telescopes joining the chase, each adding pixels to a growing portrait. The object brightens as it nears perihelion but never sprouts a tail. It's as if sunlight touches it and slides off, unacknowledged. The official statements grow more cautious, the words anomalous reflectivity and non-gravitational acceleration popping up like shy mushrooms. You imagine being part of the team, sleep-deprived, exhilarated, fingers trembling as you check the coordinates. There's a strange intimacy in chasing something so far away. Every frame feels like an invitation. Every data gap feels like rejection. It's unrequited cosmic love, pure and simple. A brief moment of levity breaks the tension. One intern, apparently overtired, edits a calibration script to label the target Guess 003. The nickname sticks. Soon everyone's using it. Guess 003 magnitude's up by half a point tonight. Guess 003's on schedule for next pass. It sounds so casual, like the universe just RSVP'd. You lean closer to the simulated feed. Guess 003 drifts silently across a field of stars, its motion almost defiant in its calmness. There's no flicker, no spin signature, no signs of venting gas. And yet, when they compare frames across different telescopes, the background starlight appears slightly off, like the object bends light around it in faint, inconsistent ripples. Could be atmospheric distortion, could be lens calibration, or, it's fine, you tell yourself, it could be something else entirely. Meanwhile, chatter spills through academic circles. Is this really the third? Or have we missed dozens more too faint or too fast to spot? One researcher points out that ATLAS only catches a fraction of potential intruders, Space is vast, our sensors tiny. Another counters that the odds of 3 detections in less than a decade are suspiciously high. The implication hangs unsaid. Maybe the visitors are coming in clusters. As the days pass, you sense the atmosphere around the discovery change. Excitement turns to caution, then to unease. Public releases grow sparse. Someone mentions data inconsistencies and pending validation. The object continues its journey inward, heading toward perihelion at just under 1 astronomical unit, nearly crossing Earth's orbital path. Amateur astronomers try to catch it, but it's faint and elusive, visible only through long exposures. In one of those images, maybe a coincidence, maybe not, the background shows a faint geometric pattern, a hexagonal ghost in the noise. Most call it an artifact of compression. You, though, have your doubts. By the second week, the ATLAS system has logged more than 100 observations. A routine by now, but somehow every new data point deepens the mystery. The orbital model refuses to settle. The curve keeps twitching like a heartbeat under the skin of the solar map. Someone jokes that it's breathing, and everyone laughs a little too loudly. You stand under the digital stars trying to picture the real object as it races through the void. Cold, small, maybe ancient beyond reckoning. You wonder if it carries dust from worlds whose suns have already died. Or maybe it carries questions instead, written in whatever passes for ink between galaxies. A gust of mountain air brushes your imagination. The telescopes hum, their mirrors catching the last shimmer of twilight. The object is out there somewhere, indifferent but watchful. And as the data streams home, you can almost sense it noticing, ever so slightly, that we've noticed it back. You lean over a holographic solar map, lines of orbit looping like ribbons of spun glass. Every planet and comet behaves as expected, elliptical, predictable, gravitationally polite. And then there's the wild scribble of 3I/ATLAS, a path so strange it looks like someone sneezed while drawing it. You watch the simulation run again. The object cuts across the plane of the solar system at an angle that almost feels intentional, skimming past Mars' orbit, dipping inward toward the Sun, and then slingshotting back out. Not north, not south, but sideways, like a skipping stone that suddenly decides water is optional. The mainstream fact is simple enough to state and maddening to explain. 3I/ATLAS follows a hyperbolic trajectory with an eccentricity of roughly 1.16. Anything over 1.0 means it isn't bound to the Sun, it came from somewhere else and will never return. But the anomaly isn't just that it's hyperbolic, it's that the inbound vector doesn't trace neatly back to any known stellar stream. Most interstellar objects we've modelled seem to flow from the direction of the solar apex, the point toward which the Sun moves in our galaxy. 3I/ATLAS ? It came in from an oblique angle that aligns with nothing. No galactic plane, no known current, no easy story. Astronomers try to describe it in polite mathematics. They call it non-coincident with established velocity dispersions. What they really mean is, we don't know where it came from, and that's annoying. You picture Newton again, tugging at his wig, muttering something unprintable in the 17th century English. There's a lovely irony here. Gravity, our oldest cosmic truth, works flawlessly on paper, yet 3I/ATLAS seems to treat it like a suggestion. When plotted backward, its path intersects the Oort cloud in a way that makes the simulation flicker, as though the object briefly hesitated there before committing to entering the solar system. Of course, that's nonsense. Rocks don't hesitate. But the models show what the models show. You stare at the faint digital blip where the hesitation occurs, like a comma in the sentence of its flight. A quirky tidbit from the archives. In the 1960s, when computers were the size of rooms and storage meant magnetic tape, NASA's JPL accidentally simulated an impossible orbit that looped backward in time. It turned out to be a rounding error. The engineer who found it jokingly wrote, "Object 0, disobedient." The note survived decades later, a reminder that sometimes the universe doesn't need to be weird, our math just gets sleepy. You wonder if 3I/ATLAS is just another disobedient object, or something less forgiving. Historians still argue whether the great scientific revolutions, Copernicus, Newton, Einstein, happened because people sought simplicity, or because nature forced them to. Maybe 3I/ATLAS is another shove from the cosmos, a gentle reminder that our neat diagrams are still doodles in the margins of something larger. In the labs, the numbers continue to misbehave. Each new observation refines the trajectory slightly, but the refinements never converge. The object's path jitters subtly, like it's being nudged by invisible hands. Radiation pressure? Possibly, but the math doesn't balance. Solar wind should have shoved it outward more strongly, yet the deviation sometimes goes inward. You stare at the residuals graph, a spiky line that looks suspiciously like an EKG again, and can't help thinking of heartbeat metaphors. You imagine yourself floating alongside it, a ghost companion trailing this visitor as it arcs past the inner planets. There's no sound, only a faint shimmer as sunlight glances off the surface. It's smaller than you expected, smoother too, no jagged edges, no chaotic spin. You reach out mentally and sense cold, clean geometry. The thought crosses your mind that maybe it was shaped, not formed. Then you scold yourself. That's the same dangerous path that led people to call Oumuamua a spacecraft, but curiosity is louder than caution. One night, a team at the European Southern Observatory publishes preliminary non-gravitational acceleration data. They're cautious, scientists always are, but buried in the appendix is a note. Anomalous component detected along the radial vector. Translation: it seems to push toward the sun, as if it wants to dive deeper before escaping. The data isn't conclusive. A calibration error could do it, or maybe not. Across online forums, enthusiasts start drawing comparisons to Project Daedalus, the 1970s theoretical design for an interstellar probe that would use fusion micro-explosions for propulsion. You chuckle softly at the thought. Humanity still can't keep coffee machines running past warranty. Yet here we are accusing other civilizations of casually lobbing starships around. Still, there's something poetic about it. Our species sees an odd trajectory and instantly assumes intent. Maybe that's what separates us from the rocks. We can't stop writing stories. Late in the simulation night, a new dataset arrives from an observatory in Namibia. You lean closer. The trajectory line shifts again, ever so slightly, bringing its outgoing vector into near alignment with Earth's orbital plane. Statistically meaningless, probably coincidence. But coincidences have a way of stirring the human mind like a spoon in deep water. The forums light up. "It adjusted course," someone posts. "They're watching us," replies another. Then a third comment, calm and matter-of-fact. "No, it's gravity's way of winking." Somewhere, a graduate student jokes about naming the anomaly Newton's wink. You imagine that phrase etched in future textbooks, next to an asterisk and a very long explanation. Outside, clouds drift across your imaginary night. You can almost hear the telescope motors hum as they track the object's invisible path. Inside, you feel that quiet awe, the kind that makes your chest tighten, not from fear, but recognition. The universe, once again, is bigger than promised. You zoom the simulation back until the entire solar system fits in your palm. There, 3I/ATLAS is a faint silver thread, crossing and departing, leaving behind a whisper of altered math. You can't help wondering if, in some other distant star system, another civilization is looking at a similar chart, tracing our debris, asking the same trembling question. Where did that come from? You drift closer now, not in body but in imagination, sliding through the cold void until the faint gleam of 3I/ATLAS fills your view. It's small, unassuming, and yet somehow too deliberate. The sunlight that touches it scatters in ways that don't make sense, refusing to behave like light hitting a dusty comet. You watch the reflection graph unfurl on a screen, lines climbing and dipping like slow waves, each colour a clue to its composition. This is spectroscopy, the cosmic fingerprint test. You hold your breath as the first results scroll in. Here's the mainstream fact. Every object in space leaves a signature when starlight bounces off it or passes through its gas. Astronomers break that light into spectra, bands of colour marked by thin, dark lines where specific elements absorb energy. Those lines are the universe's barcodes: hydrogen, carbon, sodium, water, iron. Simple, elegant, predictable, until now. Because when Atlas and a dozen other telescopes turned their prisms toward 3I/ATLAS, the resulting spectrum looked wrong. Not just unusual, unclassifiable. The absorption lines didn't match any known combination of minerals or ices. Some wavelengths were muted as though the surface swallowed light rather than reflecting it. Others flared brighter than expected, spiking in near-infrared bands associated with complex organics, except too evenly distributed to be natural. You can almost hear the astronomers sigh through their keyboards. One frustrated graduate student posted a late-night message on the project's internal forum. "It's like we're shining a flashlight on velvet that glows back." The phrase stuck, passed around quietly among the research teams. Velvet that glows back, a poetic way of saying physics is shrugging. Historians still argue whether anomalies like this drive progress or paranoia. Some claim the 19th century discovery of spectral lines in stars gave birth to astrophysics itself, a moment when light revealed chemistry across the void. Others note how each anomaly tends to breed new conspiracy. When we don't understand, we invent purpose. You smile at the irony that science and storytelling are siblings arguing over custody of wonder. The data gets rechecked. Calibration lamps, instrument drift, detector noise, every usual suspect lined up. But the weirdness remains. A faint plateau appears near 2.3 micrometers, the same spectral region where methane ice would normally absorb, yet 3I/ATLAS isn't cold enough to preserve methane. Something else must be mimicking it. Silicon composites? Exotic carbon allotropes? Someone half-jokingly adds dark paint to the spreadsheet. And then there's the ultraviolet side of the spectrum, a clean, featureless slope. No dust scattering, no irregular dips from complex molecules. Just smooth light, like a mirror polished to perfection. You imagine running your hand along its surface, the way one might trace frost on glass, expecting texture but finding none. Maybe it's a rock wearing a mask. A quirky tidbit surfaces during one of the nightly cross-checks. Data from a smaller observatory in Chile shows a faint emission feature, a narrow spike repeating every 26 hours. Too slow for rotation, too fast for orbital modulation. It could be a reflection artifact, or it could be something weirder, a timed release of gas or energy, like an exhale. The team jokes that the rock has a sleep schedule. You chuckle along, but deep down the phrase timed release curls uncomfortably in your thoughts. Meanwhile, in the conference rooms of observatories and universities, the debates start turning personal. One camp insists it's a carbonaceous asteroid with an unusually smooth crust, rare but possible. Another camp argues that the reflectance patterns hint at layered material, maybe even engineered. A senior spectroscopist sums it up neatly. Either it's a new type of rock, or it's not a rock. You imagine the atmosphere in those meetings, the stale coffee, the flickering projector, the quiet thrill of standing at the edge of the known. Someone drops a laser pointer, and the red dot rolls across a chart like a wandering planet. A nervous laugh follows. Every discovery feels like this at first. Exhilarating, terrifying, absurd. Outside the human world, the object spins. Or maybe it doesn't. The light curve suggests it rotates once every few days, yet the reflected brightness stays strangely constant. If it has facets or irregularities, they're hidden beneath a uniform shell. You think of stealth aircraft, their surfaces angled to scatter radar. Only here, the scattering is of sunlight, and the enemy is curiosity itself. By the time June arrives, teams around the globe are pooling resources for continuous monitoring. The James Webb Space Telescope takes a turn, its infrared sensors peering into the dark like an ancient oracle. The resulting image, released quietly, shows a dim oval glow with a spectral gradient that shouldn't exist. Colder at the center, warmer at the edges. That defies thermodynamics. Heat doesn't gather at the edges of airless rocks, it diffuses. Unless, of course, the edges are something else. A fringe YouTube channel seizes on that photo, adding ominous music and the caption, "It's not reflecting, it's transmitting." Normally you'd roll your eyes. Tonight, though, the thought lingers longer than it should. If something about the surface interacts with sunlight that way, maybe it's doing more than shining, it's talking. In ancient times, the Mayans watched Venus for its phases and called it the great star that breathes light. To them, light was communication, a language written in radiance. Historians still argue whether those myths describe astronomy or allegory, but the phrasing feels apt now. You watch the spectral graphs flicker across the monitor and think, yes, maybe this rock is breathing light. You picture yourself floating in front of it, the void stretching forever, the sun a distant lantern. The object's surface gleams faintly, not silver, not grey, but some impossible shade that shifts with your gaze. You lean closer, and for an instant the reflected sunlight trembles, almost like an eye dilating. Then it's gone, back to silence. You blink, shake off the dream. Just data, you remind yourself. Just photons bouncing off something old and indifferent. But even the scientists start using softer language now. Reflectivity cycle, spectral pulse, transient emission. The vocabulary of observation slipping toward the vocabulary of heartbeat. And deep down, a small, irrational part of you wonders whether 3I/ATLAS is looking back through the same wavelengths, studying our reflected light, tracing the colours of our curiosity. Maybe to it, Earth's glow looks just as strange, blue and restless and full of questions. The universe, it seems, doesn't mind being a mirror. You float alongside 3I/ATLAS as sunlight pours over it like slow honey, and what strikes you most is its colour, or rather, its refusal to have one. Even in enhanced images, the thing looks stubbornly uniform. No mottled patches, no bright spots, no dark seams where craters might hide. Just an even, matte tone, a sort of non-colour that seems to absorb attention more than light. It's the visual equivalent of silence. The mainstream fact, reflectance data gathered from multiple observatories confirms that 3I/ATLAS maintains a near constant albedo, about 0.12 across its entire rotation. For comparison, most asteroids show albedo variations of at least 20% as they spin, comets even more. To stay that consistent, the surface must either be incredibly smooth or covered in a material with uniform reflectivity, like graphite dust or finely compacted regolith. But regolith requires weathering, and interstellar space doesn't do weather. You watch scientists squint at the same graphs, their eyebrows describing new equations of confusion. The object is as colourless as ash, yet gleams faintly blue-grey under solar illumination. When the data from the European Southern Observatory merges with infrared readings from Webb, a pattern emerges, or tries to. The visible spectrum suggests a rocky composition, but the infrared hints at something metallic. A cosmic mullet. Business rock in the front, reflective metal in the back. And then the real head-scratcher. Polarization. When light bounces off surfaces, it becomes polarized. Waves align depending on texture and angle. Plot that polarization against phase angle, and you can tell a lot about what you're looking at. But 3I/ATLAS's polarization curve is almost flat. No peaks, no valleys. It's as though the object politely refuses to tell us which way its surface tilts. One weary postdoc types into a group chat, either it's made of microscopic billiard balls or it's cheating. You grin. Cheating sounds about right. Historians still argue whether the obsession with cosmic colour began with Galileo or with Instagram. Humans have always needed hues to feel real. Mars had to be red, Neptune blue, Pluto pale gold. Yet the deeper we look, the more the universe insists on ambiguity. 3I/ATLAS is the newest chapter in that argument, a rock that defies palette. A quirky note buried in one instrument report adds spice to the mystery. During a calibration sweep, an adaptive optics system detected a faint interference pattern, a set of concentric rings not centered on the object but offset by a few meters. Normally that means atmospheric turbulence, except this was space-based data. No atmosphere, no turbulence. When engineers replayed the raw images, the rings pulsed faintly, almost rhythmically before fading. Someone dubbed it the halo glitch. The term stuck long enough to spawn a meme or two before being quietly scrubbed from official summaries. You imagine what it would feel like to see that halo through an eyepiece, the object framed in a soft, impossible glow, like a saint's icon rendered in photons. You'd probably whisper, even if no one else were around. Back on Earth, laboratories start building models. 3D printed shapes, computer-rendered surfaces, simulated scattering patterns. All of them fail. A group at MIT proposes the idea of optically coherent dust armor, a fancy way of saying maybe the rock is coated in a layer of nanoscopic crystals that reflect light uniformly. The phrase catches on because it sounds satisfyingly science-fictional. You roll it around in your head. Dust armor has a nice ring to it. Meanwhile, online speculation blooms like mold in a damp basement. One camp swears it's a fragment of an ancient Dyson sphere, polished smooth by cosmic radiation. Another claims it's an alien monolith designed to appear boring until approached. A third insists it's natural, just the most symmetrical, boring rock in existence. Everyone seems to agree on one point. Boring shouldn't be this exciting. You chuckle softly, thinking of all the times humanity mistook uniformity for serenity. The moon looks grey until you land on it and realise it's a chaos of glass and dust. Jupiter's clouds look smooth from afar but hide storms the size of continents. Maybe 3I/ATLAS's calm surface conceals its own turbulence, just one layer beneath perception. As days pass, the colour data continues to defy expectation. Photometric measurements under varying solar angles reveal that its hue barely shifts, suggesting a surface that scatters light isotropically. That's fancy talk for, it doesn't care where the sun is. Most natural objects display at least a touch of shading. Even charcoal looks lighter where it's sunlit. But here, the light seems to disappear evenly across every angle, as though the surface refuses to acknowledge directional physics. A professor in Cambridge presents a talk titled The Colour of Confusion, 3I/ATLAS, and the Problem of Perfect Surfaces. You can tell she's enjoying herself, half academic, half artist. She ends the lecture with a slide showing a blank grey square and the caption, "Sometimes the absence of detail is the detail." The audience claps. You clap too, even though you're watching the stream at 2 a.m. with the sound low enough not to wake anyone. In the darker corners of the internet, someone posts an enhanced composite image claiming to reveal a faint geometric pattern etched into the surface, hexagonal, repeating, almost architectural. Mainstream astronomers dismiss it instantly as compression noise, and rightly so. Still, the pattern haunts you. You keep thinking about beehives, turtle shells, Saturn's strange hexagonal storm at its pole. Nature does love a hexagon. Maybe this visitor just follows the trend. You blink and find yourself imagining colour again, despite the data. You picture faint silver ripples running under a matte exterior, as if the object were breathing beneath a thin metallic skin. The thought makes you smile. It's too poetic, too human. Yet for some reason, it feels true in a way numbers aren't. You recall that early Egyptian story about Ra sailing through the underworld on a barge made of polished obsidian, so dark it reflected the stars within itself. Historians still argue whether that myth was born from meteor sightings or from ritual imagination. You think maybe both. Maybe when something this colourless streaks across a night sky, it's impossible not to project divinity onto it. Back in the data lab, the latest readings confirm what everyone suspects. The object's spectral slope hasn't changed at all since discovery. Even after weeks of exposure to solar radiation, no alteration, no dust emission, no aging. A perfect stalemate between sunlight and surface. You stare at the report feeling that quiet unease again. In a universe where everything evolves, here's something that simply doesn't. And as you drift deeper into that thought, the blank grey of 3I/ATLAS begins to feel less like the absence of colour and more like a message written in monochrome. I am not trying to hide. I am just not interested in being seen. You rest your elbows on the console, eyes fixed on a graph that shouldn't exist. It's a line chart plotting apparent brightness against predicted gravitational tug, and it's wrong. Not catastrophically wrong. Not enough to ruin anyone's career, but just enough to make physicists squint like they've bitten into a lemon made of math. The numbers insist that 3I/ATLAS is heavier than it appears to be. The mainstream fact is clear. Astronomers can estimate an object's mass by watching how its trajectory shifts under the sun's pull, and by comparing that motion to its brightness. But 3I/ATLAS refuses to obey that neat correlation. It's too dim for the path it's carving. Based on its reflectivity, it should weigh maybe a few million tons. Based on its deflection, it behaves as though it's several times that. Somewhere between light and gravity, something isn't adding up. You scroll through the calculations. Could it be a denser material? Iron, nickel, maybe uranium-rich rock? Possibly, but the thermal readings don't support that. Could it be hollow, with mass concentrated at its core? That would fit, except that natural hollow asteroids are vanishingly rare, and a hollow structure with distributed internal mass. Well, that sounds less like geology and more like engineering. Historians still argue whether the 19th century discovery of Neptune, deduced from wobbles in Uranus's orbit, was the high watermark of pure maths triumph over mystery. For centuries afterward, astronomers trusted that invisible mass meant new worlds. Maybe that's the legacy you're seeing now, another wobble, another ghost planet that turns out to be a visitor instead. A quirky tidbit sneaks into the internal research chatter. A radar sweep from Arecibo's successor facility in Puerto Rico, yes, the one built after the old dish collapsed, returns a faint delayed echo. Nothing unusual, until someone measures the timing precisely. The return pulse arrives a fraction of a millisecond later than expected, as though it travelled through a slightly deeper gravity well near the object. Too subtle to prove anything, too persistent to ignore. The radar operator calls it the hiccup. You picture that data point glowing on a screen, a tiny blip of hesitation in the ocean of a noise. Maybe the object is surrounded by a gravitational anomaly, a dense core, or some unknown interaction between matter and radiation. Or maybe the hiccup is just the universe reminding us that precision has limits. Still, the anomaly grows harder to dismiss when another radar ping, from Goldstone this time, produces the same delay. Independent instruments, same result. It's like shouting into a canyon and hearing the echo come back tired. You lean back and imagine the possibilities. Suppose the object has a dense, heavy nucleus, surrounded by a lighter shell. Something like a planetary seed, frozen mid-formation and cast adrift between stars. A relic of a failed solar system. You could sell that hypothesis, it's poetic and testable. But then another thought creeps in, uninvited. What if the mass isn't distributed physically, but gravitationally? What if it's manipulating how we perceive weight? That's not poetic, it's unsettling. A fringe online theory coins the phrase mass without matter, arguing that 3I/ATLAS might be composed partly of exotic particles that interact with gravity but not light. Dark matter, in other words. Mainstream physicists roll their eyes. If dark matter clumped this tightly, galaxies would look like Swiss cheese. But you can't shake the allure of the idea, an interstellar shard made partly of the stuff that binds the universe together. Meanwhile, the official line remains cautious. Press briefings emphasize that no evidence suggests artificial origin, which of course convinces everyone that there might be. One scientist jokes that if they ever did find alien hardware, the first press release would say exactly the same thing. In the quieter corners of the data archive, someone runs a simulation. If 3I/ATLAS really carries extra mass, could it distort nearby spacetime just enough to alter the frequency of incoming light? The answer, surprisingly, is yes, by an infinitesimal margin. The predicted shift matches the faint redwood bias detected in several telescopic spectra. It's the smallest possible confirmation, like the cosmos whispering warmer. You scroll further down and find a note appended by a cautious researcher. Effect may indicate internal density gradient or gravitational resonance not yet understood. You smile at the phrasing. Not wrong, just not yet understood. Scientists are master poets of uncertainty. The longer you look, the more you feel the pull of this thing, not just metaphorically, but emotionally. There's a gravity to mystery itself. Humans lean toward the unknown like plants toward sunlight. You imagine floating near 3I/ATLAS, seeing its silhouette blot out the stars behind it. No tail, no debris, just smooth blackness sliding through starlight. You feel the faintest tug, a pull that shouldn't be noticeable at this distance, and realize you're drifting closer. The thought makes you uneasy, so you back away in imagination, but the tug follows. Maybe that's the problem with cosmic curiosity. You can never quite tell whether you're the observer or the observed. A fun side note. During one particularly long observation session, a software glitch caused the mass estimation script to produce a nonsense value, something like 4 × 10 to the 20 kilograms, then append a crying laughing emoji to the report. The tired grad student responsible had programmed it months earlier as a joke. When the log leaked online, conspiracy theorists naturally took it as proof that NASA found something too big to hide. You'd almost admire the creativity if it weren't so predictable. Still, a kernel of truth hides in the humour. The more we study 3I/ATLAS, the bigger it seems to become, not in physical size, but in significance. Each correction, each refinement, adds weight to the mystery. You take one last look at the simulation. The object's line through the solar system has been updated again, the outgoing leg subtly bent compared to the incoming. Not enough to alarm, but enough to whisper that gravity alone might not be steering this dance. You glance at the timestamp on the data. The change occurred while the object was nearest the sun. when solar radiation should have been strongest. Yet instead of slowing slightly, it accelerated, just like Oumuamua once did, though less dramatically. Coincidence? History repeating itself? Historians still argue whether Oumuamua's unexplained push was cometary gas or cosmic intent. Now 3I/ATLAS hums the same old tune in a slightly different key. Another uninvited guest rewriting gravity's script. You can almost hear Newton groan in his grave again. But you can also imagine him smiling too, because nothing delights a true scientist, or a sleepless dreamer, quite like a puzzle that refuses to fit. The lab is hushed tonight. Monitors pulsing soft green as streams of radar data whisper across the screen. You're leaning in again, always leaning in, as another ping from the Deep Space Network completes its round-trip journey to 3I/ATLAS. Normally, radar reflections from small objects are unromantic things, quick, tidy blips returning at the speed of math. But tonight the signal hesitates. The mainstream fact: planetary radar is precise. We bounce radio waves off asteroids all the time, timing the echo to within microseconds. That timing gives distance. The Doppler shift gives velocity. It's how we sculpt radar images of rocks millions of kilometers away. And yet the echo from 3I/ATLAS arrives late. Not by much, only microseconds again, but consistently late, as if the signal dipped through something syrupy before returning. Engineers recheck everything: transmission power, receiver calibration, atmospheric delay, all clean. The delay isn't Earth's doing. It's out there, where it shouldn't be. And that's when someone notices a second peculiarity. The returning echo is weaker than predicted, even accounting for the object's dimness. Like the surface didn't just reflect radio waves, it absorbed them. You picture that. The radar beam hitting the object, disappearing as though into velvet, and only reluctantly coughing back a faint echo. A cosmic whisper, not a shout. A quirky side note pops up from the radar lab's Slack channel. One operator types, "It's like yelling into a pillow made of physics." Another replies, "Or maybe it's answering in its sleep." The banter helps, a small human defense against the unknown. Historians still argue whether radar astronomy was the true beginning of our dialogue with the cosmos. The first radar echo from the moon in 1946 convinced humanity that space wasn't silent. It could talk back, in time delay Morse code. Maybe tonight's faint murmur is part of that same long conversation, just written in a dialect we haven't learned yet. As the night deepens, the team decides to run a frequency sweep. Multiple radar pulses at slightly different wavelengths, just to see what sticks. The lower frequencies vanish entirely, no return at all. Higher ones bounce back weakly, and weirdly enough the delay changes with frequency, like the object's surface reacts differently to different kinds of inquiry. If you were superstitious, you'd say it was choosing what to answer. The data goes quiet for a moment. You lean back, the room's hum filling the silence. Across the world, in other labs, others stare at the same numbers. There's comfort in knowing that thousands of kilometers away someone else is equally baffled. Then the waveform analyzer catches something new, a faint ripple within the return signal, an oscillation that shouldn't exist. The radar beam should scatter cleanly. Instead, there's modulation, as if the echo itself carries structure. Could be interference from the ionosphere. Could be internal reflection inside the receiver. But what if it's real? The pulse pattern repeats every 2.6 milliseconds, 10 times faster than the 26-hour brightness cycle previously observed. Too fast for rotation, too regular for noise. Someone jokes, "If this is Morse code, I'm not fluent." The radar lead smiles thinly. "Neither is the rock," she says. But still, they keep transmitting. Different frequencies, different pulse lengths, building a composite radar portrait. The resulting image, when stitched together, is faint, blurred, and yet undeniably odd. The edges fade gradually, not sharply, as though the object doesn't have a crisp boundary. You can't tell where it ends and space begins. There's a fringe hypothesis making rounds in the chat threads. Maybe 3I/ATLAS isn't solid. Maybe it's porous, a loose cluster of matter bound by electrostatic charge, like a frozen sponge drifting through sunlight. That would explain the radar absorption and the faint gravitational anomalies. It's a decent idea, except for one inconvenient truth. Porous objects usually tumble, and this one doesn't. You catch yourself wondering if you're dealing with some kind of adaptive surface, an outer shell that changes permeability depending on wavelength. A metamaterial, but cosmic. The term sounds like science fiction, but the physics isn't impossible. Humans are already experimenting with such materials on Earth. If we can design them, why couldn't nature, or something else? Out of habit, you check the latest time delay logs again. Still lagging, still faint, still stubbornly rhythmic. The radar team has started calling that pulse the heartbeat. You smirk at the name, scientists pretending they're poets again, but deep down, it fits too well. Historians still argue whether humanity ever truly believed the stars were alive. Ancient Greek philosophers thought celestial bodies possessed souls, moving in perfect harmony. Then we grew modern, called that nonsense, and built machines to prove the universe was mechanical. Now here you are, staring at an object that swallows radar and pulses in patterns, and the idea doesn't sound so foolish. By the third week of continuous tracking, the anomaly deepens. When the object crosses the Sun-Earth line, its radar echo amplifies briefly, as though the solar wind itself enhances reflection. That shouldn't happen. Charged particles scatter radio waves, not boost them. Someone posits a plasma sheath, a faint cloud around the object interacting with sunlight. But the plasma density required would glow visibly, and telescopes see nothing. You exhale slowly, the way people do when the world insists on being complicated. In the background, a soft hiss of static plays from a speaker connected to the radar feed. Normally, it's a comfort, a sound like waves on a digital beach. Tonight, though, something flickers inside it, a brief pattern of beats. 2 short bursts, one long, 2 short again. You freeze. Then it stops. Probably random. Probably. Still, you jot it down, because patterns have gravity too. Later that night, a new data packet arrives from the Goldstone relay. The headline number, the object's radar cross-section, has changed by about 3%. Tiny, yes, but impossible if the surface is inert. Something in or on 3I/ATLAS is shifting. Expanding, cracking, breathing. You lean closer to the screen, the glow washing over your face. For a moment the thought hits you, not fear exactly but reverence. The way you might feel standing in an empty cathedral, hearing a sound that shouldn't exist echo back from the dark. Maybe the radar doesn't just measure distance, maybe it's tapping on the door of something that, for the first time, taps back. And if that's true, you think, maybe it's time to decide whether you really want an answer. You sit in front of the monitor, its light soft and blue on your face, and watch as the line graphs begin to move like breathing. The data shouldn't pulse. Space rocks don't have rhythms. They spin, they tumble, they evaporate, but they don't breathe. And yet here you are staring at telemetry from 3I/ATLAS that looks uncomfortably alive. The mainstream fact is this. Brightness variation in astronomical objects usually points to rotation. When a body spins, its irregular shape or uneven reflectivity causes periodic fluctuations in the light we see. Simple, predictable. But when the light curve analysts ran the numbers for 3I/ATLAS, they found something else entirely. A slow, rhythmic pattern that repeated every 26 hours, even though there's no sign of rotation at that rate. It's as if the object subtly expands and contracts, altering the amount of sunlight it reflects. The discovery came from a team in Chile comparing back-to-back nights of data. They assumed instrument drift, recalibrated, and the pattern persisted. Then Japan's Subaru telescope confirmed the same gentle undulation, and when Webb's infrared sensors checked in, they saw temperature variations in sync with that 26-hour rhythm. Slight, only a few degrees difference, but definitely real. It's not a rotation, it's not a jet or plume, it's not solar heating, it's something else. A graduate student somewhere dubbed it the breath, half in jest, half in awe. The name stuck. Now, every night, the data updates. Inhale, exhale, inhale, exhale. You catch yourself matching your breathing to the curve before forcing yourself to stop. Historians still argue whether humans invented gods out of fear or familiarity, because they saw their own heartbeat in the pulse of the world. You can't help thinking how quickly we return to that instinct. Give the cosmos a rhythm and we start to believe it's listening. The breath defies explanation. The amplitude, the strength of the brightness fluctuation, is roughly 2%, consistent across wavelengths. If it were simply the object venting gas, you'd expect a symmetry, one side brighter, one dimmer. But this is global, uniform, synchronized. Even stranger, the infrared peak lags the optical one by about 30 minutes, meaning the temperature follows the brightness instead of causing it. You try to imagine it. A small interstellar body that expands ever so slightly, then contracts again, every 26 hours. What could cause that? A few theories make the rounds. 1. Internal thermal cycling, heating and cooling making the surface flex, but the temperature swings are too minor. 2. Microfracture relaxation, a kind of cosmic breathing caused by stress release in the material. Maybe, but the period is too regular. 3. Resonance. Perhaps someone suggests 3I/ATLAS vibrates in tune with some cosmic force. Solar magnetic fields, dark matter flux, gravitational tides, like a tuning fork humming in response to invisible music. It's poetic nonsense maybe, but you like it. The quirky tidbit that follows is almost comical. During one observation session, an overworked astronomer played ambient music through the lab speakers, slow pulses of white noise and low synth hums to stay awake. When they later analysed the spectral data from that night, they noticed the tiniest flicker in the noise residuals, exactly matching the audio tempo. A coincidence of power fluctuation, obviously, but the internet didn't think so. Within a week, conspiracy forums were calling it the reply. You smirk, imagining 3I/ATLAS tapping along to a beat from Earth, like some cosmic whale responding to sonar. It's silly, but also beautiful. The thought that across trillions of kilometers, something might be keeping time with us. A physicist from Berlin gives a talk about the rhythmic pattern, arguing it might be due to a quasi-periodic energy storage process. Solar heating charging internal capacitors of mineral structure, discharging in slow waves. Think of it as breathing without lungs, she says, smiling. The rock exhales photons. The audience laughs politely, but nobody disagrees. Back in your imagination, you hover near the object again. It's quiet here, the stars cold and sharp. You can't hear anything, of course, but you feel the pulse, a faint pressure in the emptiness, like the universe itself inhaling. The surface seems to ripple slightly, almost imperceptibly. Maybe that's what breathing looks like when done by stone. For a moment, you think of other things that pulse. The auroras, magnetars, even your own planet's heartbeat, that Schumann resonance humming faintly between lightning and air. Maybe the universe is full of lungs, some made of rock, some of plasma, all quietly expanding and contracting while we pretend we're alone. The next anomaly comes quietly. A minor calibration update reveals that the amplitude of the breath is increasing. Not dramatically, just enough to notice. Like the difference between a sleeping cat's breathing and a waking one. You whisper a small "huh" to no one. It's around then that one of the deep space photometry teams finds something else. During each expansion phase, the polarization of reflected light tilts slightly, as though the surface becomes more organized, its microscopic particles aligning for a moment. Alignment requires force. What force? No one knows. You wonder if maybe the thing wants to align. A rumor starts circulating among observers that the breathing period matches the average length of a sidereal day on Earth. 23 hours and 56 minutes, rounded by noise. It's wrong, statistically meaningless, but once said aloud, it refuses to go away. People start whispering that the visitor is syncing with us. Others joke it's jet-lagged. Historians still argue whether the human mind's greatest invention was pattern recognition or paranoia. You figure it's both. You imagine watching it through a telescope hour by hour, seeing its light rise and fall. Somewhere between the peaks, the data catches a strange subharmonic, a faint double pulse layered beneath the main one like a stutter. At first, everyone assumes software artifact, but the timing drifts slightly over days, suggesting an organic process, if organic even applies here. It's the kind of detail that doesn't make headlines but lodges in a scientist's dreams, the notion that something not alive might still have cadence. You rub your eyes, realizing how long you've been staring at graphs. Outside, the real night sky glows faintly over your window. Jupiter, a bright pin above the horizon. For a second, you think about the object out there, breathing in the dark, keeping rhythm with a planet full of listeners who pretend they're not afraid. Maybe that's the most human reaction of all, to look into the cosmic mirror and swear it blinked. And then, because you can't help yourself, you whisper to the darkness, inhale, exhale, just to see if the stars are paying attention. You let yourself drift in that imagined dark where numbers turn into shapes. The breathing curve of 3I/ATLAS fades behind your eyelids, replaced by older patterns, the ones carved into human memory long before telescopes existed. When you open your mind's eye again, the object isn't just a data set. It's a symbol floating through history's night sky. Humanity has always had a name ready for anything that wanders. The mainstream fact: every culture on Earth built stories around things that arrived unannounced from the heavens. In 1066, when Halley's Comet blazed across Europe, chroniclers called it a hairy star and took it as an omen of conquest. The Bayeux Tapestry even stitched it beside a falling crown. In ancient China, court astronomers recorded guest stars and broom stars, logging their comings and goings with the bureaucratic precision of an empire nervously watching its fate. And long before that, Babylonian priests read comets as heavenly letters, warnings, messages, invitations. You picture one of those watchers thousands of years ago standing barefoot on a ziggurat roof, tracing a white streak across the desert sky. He didn't know the math of orbital mechanics, but he knew awe, and that's the same equation you're solving tonight. The story's never really stopped. Every age reskins the same instinct. Where priests once whispered of gods, you've got bloggers posting about probes. The human brain fills silence with intention. That's our oldest survival mechanism. Historians still argue whether the line between astronomy and mythology ever truly existed, or whether they were twins separated at birth. A quirky tidbit floats up from anthropology. The Norse word farder, root of wanderer, was used for both comets and strangers. To the Vikings, a traveller from afar and a celestial visitor were linguistically the same. You smile at that, thinking how language betrays what the heart already knows. Distance and mystery are synonyms. Now, as 3I/ATLAS glides through your century, you feel that ancient reflex stirring again. Social media teems with hashtags, #ThirdMessenger, #SkyWanderer, #VelvetProbe. Someone remixes telescope footage into lo-fi music. Someone else sculpts a ceramic model shaped like a seed and calls it the breath of stone. 1,000 interpretations bloom overnight, as though humanity's collective dream machine just needed a new spark. You wander mentally through museums that haven't been built yet, their future displays glowing with holographic reconstructions. Artifacts of contact, one placard will read. Another, The Age of the Visitors, 2017 to 2025. It will hang beside a timeline of Oumuamua, Borisov and Atlas, the first trilogy of interstellar wanderers. Maybe the exhibit will include a small mirror so visitors can see themselves, a reminder that the anomaly isn't just out there, but the myths already feel alive. In an online art forum, someone posts a digital painting, a vast obsidian seed drifting between stars, threads of blue light curling from its surface like veins. The caption reads, "It carries memories of extinct suns." The post goes viral. Even professional scientists share it privately, pretending irony. You suspect they aren't immune to beauty either. Meanwhile, folklore scholars start drawing parallels to ancient stories. One points out the Maori legend of Rongomarai-Roa, a god of peace said to travel between worlds in silence, wrapped in darkness. Another finds echoes in the Dogon myths of star beings from Sirius who sink through space without wind. The details differ, but the rhythm feels familiar. The sky sends a stranger, and humanity builds meaning around the visit. You stand at your imaginary telescope again, eyes dry from staring too long. Somewhere out there, that smooth, indifferent rock, or whatever it is, continues its slow exhale. But here, on Earth, it's already transformed into story. Maybe that's our side of the bargain. The universe gives us anomalies. We pay back in myth. The irony doesn't escape you. While scientists argue over reflectant spectra, podcasters debate whether 3I/ATLAS fulfills an ancient prophecy. You hear snippets online: Third Messenger, Return of the Stone Ships, Cosmic Alignment. A few even claim to have dreamt of it before discovery, as if the subconscious keeps its own telescope. A soft chuckle escapes you. Humanity has never met a mystery it couldn't franchise. Still, a sliver of you understands the impulse. When the night is wide and silent, story is the only warmth that reaches that far. Perhaps that's why early astronomers gave comets personalities. Long hair, tails, tempers. Maybe tonight's mathematicians aren't so different. They just use error bars instead of epics. You recall that one scholar's comment buried in an interview: Every anomaly is a kind of myth waiting for equations. You liked that line so much you wrote it down. Maybe 3I/a TLAS is just the latest myth in the making, a bedtime story for a species afraid of cosmic quiet. In your mind's eye, the object drifts above ancient Earth. The pyramids glint faintly beneath it. The Greek philosophers point. The Chinese court scribes ink their bamboo slips. The Mayan priests chant numbers that almost match its orbit. Time folds for a moment, all those watchers overlapping, all of them looking up at the same unknowable guest. And you, another watcher, whisper into the digital dark, "We see you." For a second, it feels like the light curve responds. The breath, timing itself to your pulse. You laugh softly, because of course it doesn't, but the comfort lingers. Maybe connection is the illusion that keeps us sane. As dawn creeps through your window, you realize that 3I/a TLAS isn't just bending physics, it's bending history, pulling ancient wonder through the needle's eye of modern science. The same awe that once built temples now fuels cloud storage. The same longing paints equations instead of walls. Somewhere, an early civilization would have called this a god. You just call it data, but you still stare at it the same way. Head tilted, breath held, waiting for meaning to shimmer in the noise. Maybe that's the only constant in all of astronomy, the heartbeat of curiosity echoing between ages. And tonight, you're part of that lineage. One more mortal turning cold numbers into firelight. The rhythm of myth fades as the present world snaps back into view. You're no longer on a ziggurat or inside a temple. You're in a conference room, the modern kind. Walls beige as fatigue, air conditioning too ambitious, a coffee pot doing its best impression of an event horizon. The screens at the front of the room flicker with plots and equations, and the scientists sitting around the table look half awake, half electrified. They've been running numbers all night and the numbers have started fighting back. The mainstream fact, scientific debate is supposed to be polite. Peer review, data sharing, further study required. But behind the PowerPoints and disclaimers, there's always emotion. Curiosity is competitive, discovery, territorial. And 3I/a TLAS has now achieved what few objects ever do. It has split the global astronomical community straight down the middle. On one side are the conservatives. It's a natural object, they say, albeit with exotic materials, maybe a chunk of a shattered exoplanet polished by eons of cosmic radiation. Its weird orbit, just a lucky trajectory, its breathing light curve, thermal flexing, the radar anomalies, instrument noise. There's always a rational explanation if you're patient enough. On the other side, the radicals. They're not wearing tinfoil hats, not yet, but their eyes are bright in that slightly haunted way that means they've started wondering dangerous things. They point out the cumulative oddities, the smooth reflectivity, the delayed radar echoes, the rhythmic pulse, the anomalous mass. One or two of them even whisper the forbidden words, self-regulating system. Historians still argue whether Galileo's trial was the birth of the modern science, or a cautionary tale about what happens when wonder scares authority. You can almost hear that argument echoing now across the room. Someone clears their throat and clicks the next slide, a time series showing the object's changing velocity. "It's accelerating," she says flatly, "not by much, but consistently. Radiation pressure can't explain it." Her colleague shakes his head. "Thermal outgassing," he counters, "invisible jets. Same as Oumuamua." She sighs. "Then where's the dust?" A murmur ripples through the room like a low tide. The projector light catches coffee steam and turns it into a miniature nebula. You almost expect the object itself to materialize out of it, hovering between arguments. Then comes the phrase no one wants to say, but everyone's thinking, propulsion. It's spoken quietly, almost tenderly, like invoking a ghost. The room stills. You can sense the immediate recoil, the instinctive, professional need to reject the extraordinary. "We don't have evidence for that," someone says. "We barely have evidence for anything." And yet, silence lingers longer than it should. Outside the walls of academia, the conversation is louder. Online forums light up again. News anchors smirk through segments about the rock that might be running on batteries. Memes bloom. Grainy photos of 3I/a TLAS with captions like "Solar System?" Never heard of her. A quirky side story emerges when an independent research group in Finland claims their amateur radio array has detected faint sideband emissions near the object's radar frequency. They call it resonant backscatter, a term that sounds impressive but means little without context. The data is noisy, ambiguous, but the press loves it. By morning, a headline declares, "Scientists detect possible signal from interstellar object." You groan. Scientists pluralized is always the death of nuance. Back in the official channels, a handful of researchers attempt damage control, releasing carefully worded statements about unverified phenomena. They use phrases like instrumental artifacts and frequency harmonics, which are true but also dull. Dull rarely wins against wonder. You lean over your coffee and stare at the live telemetry feed projected on the side wall. There's the object, a tiny white trace crossing a digital sky. Every few seconds, new data trickles in. Velocity, magnitude, position. The numbers blur into a rhythm you almost recognize. Maybe that's what's unnerving. It's not chaos, but consistency. The anomalies don't fluctuate randomly. They repeat like clockwork, as if the object follows a schedule. Historians still argue whether Kepler's discovery of orbital harmony was mathematics or music. The solar system, after all, moves in ratios and resonances. Maybe 3I/ATLAS is humming its own tune. In the corner, someone mutters that the next step should be to ping it again with radar, longer bursts this time. Another suggests using optical lasers to test for reflective modulation. A third, perhaps joking, proposes broadcasting a message. If it's going to keep waving, we might as well wave back. Laughter follows, but it's nervous laughter, the kind that cracks around the edges. You can almost feel the divide widening, not just between skeptics and believers, but between data and meaning. Science thrives on uncertainty, but humans crave conclusion. And 3I/ATLAS keeps offering just enough evidence to keep both sides restless. Later that night, in an online conference chat, someone posts a poetic observation. Maybe it's not an object at all, but a behaviour. The line garners a dozen thinking face emojis before the thread dies. You jot it down anyway. The debate stretches into dawn. Some participants leave the call exhausted. Others stay, eyes glazed but minds burning. You find yourself imagining this argument happening not just here but centuries ago, every time a new celestial anomaly appeared. Tycho Brahe insisting comets were atmospheric, Kepler arguing otherwise, Newton trying to reconcile faith and force. The faces change, but the pattern doesn't. Discovery, denial, debate, wonder, fatigue, then repetition. As the session finally ends, the moderator sighs, rubs his temples and says the words that will inevitably become tomorrow's headline. We are not ruling anything out. And with that, the room exhales, relief mixed with terror. You step outside into pre-dawn air. The real sky stretches above you, calm and vast, utterly indifferent to human squabbles. Somewhere up there, 3I/ATLAS glides past Venus's orbit, still breathing, still accelerating, still unclassified. You look up and whisper, "They're arguing about you." For once, the silence feels amused. You find yourself slipping into a simulation. Nothing fancy, just a swirling sea of code and digital starlight. The real 3I/ATLAS is far beyond any camera now, but the data lives here, in models and matrices. Hundreds of computers across half the planet are running virtual clones of it, each one slightly tweaked, each one performing an invisible ballet inside a silicon sky. The mainstream fact: this is how modern astronomy works. Observation gives you snapshots, simulation gives you motion. With enough physics, you can make the universe dance on a screen. Every variable, density, rotation, composition, solar wind pressure, can be tuned, tested and argued about until the model finally sings the same tune as reality. Except this time, no tune fits. You stand at the edge of the simulated solar system, watching 1,000 blue dots, possible 3I/ATLASES, fly in from interstellar space. Most behave like good physics students, slingshotting past the sun and out again in tidy arcs. But a handful of them drift sideways, bend oddly, stall before escaping. The simulation code marks them in red. Those red dots are the nightmares. Even the best-fitting model still leaves residuals, tiny mismatches between prediction and observation. Normally those are random noise, but here they pulse. When plotted over time, The residuals echo that same 26-hour cycle, as if even the math is breathing. Historians still argue whether computers liberated science or just replaced paper mythology with digital ones. A 20th century astronomer once warned that simulation is only reality's echo, and tonight that echo feels hauntingly literal. The quirkiest discovery comes from a researcher in Prague who runs a chaos analysis on the trajectory data. Chaos theory is supposed to quantify unpredictability, but her output graph shows structured oscillations, patterns that look eerily like feedback control. She double-checks the code, assuming a bug. There isn't one. When she publishes the preprint, the title is dry. Nonlinear perturbation analysis of 3I/2025-01. But the abstract reads like poetry. The system appears to resist divergence. Resist divergence. In plain speech, the thing corrects itself. You imagine the object gliding through space, adjusting fractionally as the sun's gravity tugs, like a fish flexing its fins against a current. Maybe that's coincidence. Gravity plus spin plus radiation pressure. But maybe it's something deeper, an emergent order built into matter itself. The simulation teams start getting creative. One adds internal density gradients, another tries magnetic field coupling. A third, half in jest, introduces a feedback algorithm, a line of code that lets the simulated object nudge its own trajectory towards stability. The result? The graph matches the real data almost perfectly. You stare at the screen, and for a second, your scalp prickles. No one says the word intelligence, not yet. But the silence around it hums like static. You glance over the shoulder of the graduate student running the experiment. Her screen glows with numbers scrolling like rain. She bites her lip and murmurs, "It's like it knows where it's supposed to go." Then she quickly adds, "I mean, mathematically." Of course she means mathematically. Nobody wants to sound like a crank. Still, the hypothesis begins to spread quietly through academic channels. Maybe 3I/ATLAS isn't a single object, but a coherent swarm, a cloud of ultrafine fragments bound by electromagnetic forces, acting as a single unit. That could explain the mass discrepancy, the uniform colour, the radar absorption. It could also explain the breathing, if those particles expand and contract rhythmically in response to sunlight. A natural process, but one that looks designed. The idea finds supporters and skeptics in equal measure. Someone jokes that it's space slime. Another counters that it's the most elegant slime in history. You laugh with them, though the unease lingers. A fringe conference paper from a private research lab pushes further, comparing the feedback patterns to something known in engineering as PID control, proportional integral derivative algorithms used to keep drones stable. The math fits disturbingly well. When someone points that out on a live stream, the comment section explodes. Half the viewers scream, "Aliens!" The other half scream, "Bad statistics." You rub your eyes, half expecting the simulation to freeze. Instead, it pulses again. Each iteration of the model edges closer to reality, but never perfectly. It's as if the object itself moves goalposts just out of reach. In another corner of the internet, digital artists start animating their interpretations. One viral clip shows a shimmering lattice structure flexing like a jellyfish, trailing photons as it swims through space. The caption reads, "Self-stabilizing seed." You watch it twice. It's absurdly pretty. Historians still argue whether aesthetics has any place in science. Kepler called planetary orbits the music of the spheres, while Newton scolded him for sentimentality. Yet here you are, staring at an animation that feels truer than equations. Maybe beauty is just the universe's way of teaching comprehension. Then, buried deep in one dataset, a programmer finds something bizarre. Every time the simulation recalculates after an update, it generates a checksum, a string of random digits ensuring data integrity. Except now, those checksums aren't random. The trailing numbers start forming a repeating sequence. 3141592, pi, coincidence, obviously. The human brain finds patterns where none exist. But the rumour escapes anyway. 3I/ATLAS is talking in math. By morning, 1,000 Twitter accounts are decoding nonsense. The lead simulation engineer tweets a single line in reply. If the cosmos wanted to send a message, it wouldn't use our checksum format. Then he deletes his account for a week. You step back from the glowing model, exhaustion settling over you. In the silence, the hum of the processors sounds almost oceanic. The simulation world stretches before you. Virtual stars, virtual dust, a virtual rock that refuses to behave. Somewhere in that synthetic void, the model's colour shifts, just slightly, toward the blue end of the spectrum. Probably an automatic exposure adjustment, you tell yourself. Probably. But as you watch, the object in the simulation breathes again. A pulse of light, soft as sighing. And for the first time, you imagine, not fear, not invasion, but a kind of patience. Like something waiting for us to stop simulating and start listening. Maybe you think the universe doesn't just allow anomalies. Maybe it needs them. Cracks in certainty where wonder can slip through. The models keep running. The processors hum their lullaby of numbers. And you, caught between physics and poetry, can't tell whether you're debugging reality or dreaming it. The simulations fade from your eyelids like afterimages from a flashbulb, and you find yourself listening, really listening to the noise. The hum of servers, the faint static from a radio feed on another monitor, the soft tap of a cooling fan's rhythm. It's all sound, all signal, all waiting to be translated. And somewhere inside that static hides 3I/ATLAS again, still whispering its strange pulse across the void. The mainstream fact: when astronomers collect photometric or radar data, there's always background noise, cosmic rays, solar wind, Earth's own magnetosphere. Every measurement is a sea of hiss, but sometimes, inside that hiss, you find patterns. Pulsars were discovered that way in 1967, when Jocelyn Bell Burnell saw perfectly timed blips and jokingly labelled them LGM1, little green men. The joke turned out to be neutron stars, but the wonder stuck. Tonight feels like that kind of night. You scroll through the spectrogram, a rainbow graph of time and frequency. Most of it looks ordinary, but a faint ridge repeats every 26 hours, the same period as the breath. It's weaker than background, buried almost below detectability, but it's there. You overlay data from 3 separate observatories, and the ridge aligns. That shouldn't happen unless the pattern is real. At first you think it's instrumental crosstalk, then you filter out all human-made frequencies, and the ridge remains. When you slow it down, you realize the amplitude modulates gently, rising, falling, like Morse code whispered through fog. A quirky detail. One of the postdocs turns the spectrogram sound file into audible range, just to check for interference, and pipes it through the speakers. What fills the lab is a low tidal hum punctuated by soft clicks. It sounds uncannily like breathing through a snorkel. Everyone laughs nervously, pretending it's nothing, but no one turns it off. Historians still argue whether the first radio astronomers were scientists or accidental musicians. Maybe both. Tonight, you understand why. The cosmos has rhythm, and sometimes the only proper response is to listen. The team dubs the phenomenon the echo pattern. Officially, it's electromagnetic interference. Unofficially, it's hypnotic. You leave the recording running while you sip cold coffee, the clicks syncing perfectly with your heartbeat. Every time you think you've lost the pattern, it returns, patient, polite, undeniable. At 3:14 a.m, the feed spikes. A sharp triple pulse rises above the baseline, evenly spaced, then silence. The system logs it as an instrumental anomaly. You log it as a shiver. You replay the segment again and again, zooming in until the waveform fills the screen. 3 beats, nothing more. Could be random, could be coincidence. But then you notice something subtle. Each pulse carries a harmonic at exactly twice its frequency, an octave. That's not common in random noise, that's structure. Someone jokes that 3I/ATLAS just said hello. Someone else mutters that if it did, we should probably pretend we didn't hear. Outside the lab, news cycles churn on. Space agencies issue calm updates about ongoing photometric analysis. Bloggers write headlines like, "Is the third messenger singing?" A musician in Berlin remixes the signal into ambient techno. It climbs the charts for a week. Humanity, ever consistent, makes art before answers. Meanwhile, the data keeps whispering. The 26-hour pattern tightens, its peaks sharpening as the object drifts farther from the sun. Radiation pressure should weaken it. Instead, the amplitude grows. If this were purely thermal, it should fade. Instead, it clarifies, as if distance brings focus. You imagine 3I/ATLAS out there, sailing past Mars's orbit now, shrinking to a single pixel in telescopic vision, yet somehow louder in every frequency we have. The paradox feels deliberate, like it wants to be noticed even as it leaves. A fringe theory blossoms overnight, that the object converts solar energy into modulated magnetic fields, essentially pinging us. Another claims the signal carries encoded data, a Fibonacci sequence, binary primes, the usual suspects of wishful thinking. You check the math. It's not Fibonacci, it's not prime, it's just balanced. The intervals form a smooth ratio that feels intentional, but resolves into nothing when decoded. Maybe that's the point. Maybe ambiguity is the message. A fun yet eerie anecdote surfaces from an amateur observer in Argentina. He'd left his radio telescope streaming live to his YouTube channel. When the triple pulse event occurred, his viewers flooded the chat with reports that their smart speakers momentarily glitched, volume knobs flicking, LEDs pulsing 3 times. Coincidence, clearly. Still, the clip racks up millions of views under the title, "When the Sky Knocked." You sigh and close the browser. Humans and myth again, looping like old film, yet privately you replay that hum one more time before shutting down the console. Through headphones it's almost soothing. There's structure without meaning, repetition without message, like waves against a hull, like breathing in sleep. Historians still argue whether the universe is fundamentally noise or music. Maybe both, you think. Maybe 3I/ATLAS sits right on that boundary, a cosmic metronome counting something larger than comprehension. You picture it gliding silently now, its surface cool, its pulse steady. Each breath carries photons outward, scattering through emptiness, crossing the light of Jupiter, threading between dust and radio whispers until some tiny fraction reaches Earth, and you. The signal fades, then swells again, and you realize you've begun to anticipate the next beat, the way one waits for a heartbeat between stethoscope and skin. You whisper to the speaker, half embarrassed, "We hear you." Nothing answers, but the next pulse arrives a little sharper, as if a reply was simply made of timing. You sit back, smiling at your own foolishness. It's not proof of life, you remind yourself, it's just data. Still, the thought refuses to fade. What if all that time we spent searching for messages from the stars, listening for someone else's voice, was backward? What if the universe sends patterns instead of words, and intelligence is measured by who learns to dance with them? The speakers hum again. You close your eyes, count 3 pulses, and feel very small, very awake, and strangely comforted. You wake late in the day to find the world arguing. That's not new, of course, but the flavour of argument has shifted, less academic, more conspiratorial, like static that suddenly learns to rhyme. The 3I/ATLAS echo pattern is everywhere now, climbing from scientific preprints into headlines and hashtags. A week ago, the mystery was safely locked inside observatories. Now it's spilled into living rooms and comment sections where logic goes to take naps. The mainstream fact: every great discovery drags along its own chaos. The first radio burst from space, the face on Mars, even the early moon landings, all became battlegrounds between skepticism and spectacle. Science thrives on patience, but the internet does not, and tonight both worlds have collided. You scroll through the avalanche of posts. Some claim the object's signals are deliberate communication, others insist it's a government hoax, a publicity stunt to distract from earthly problems. A few suggest it's not in space at all, but a holographic projection in low orbit. One even declares it's the second coming, though their math seems a little forced. In the middle of this digital maelstrom, a real problem brews quietly. Someone at one of the observatories, no one will say who, has deleted a batch of radar logs. The official statement blames data corruption. Unofficial whispers say the entries were pulled manually. The missing files cover precisely 12 hours around the time of the triple pulse event. Convenient. You close your laptop, lean back, and stare at the ceiling. This is how stories fracture. One missing log, and suddenly the whole world fills the gap with imagination. A quirky tidbit emerges from an older astronomer on a podcast. When Galileo first saw the moons of Jupiter, he says, the Church didn't deny they existed. They just didn't like what they implied. He chuckles softly. Nothing's changed. Historians still argue whether suppression in science comes from fear of being wrong or fear of being irrelevant. You suspect it's both. The deleted data becomes the week's obsession. Hashtags shift from third messenger to missing hours. Hackers swarm the servers of major observatories, looking for hidden files. Anonymous Twitter accounts claim to leak screenshots. Half of them fake, half of them probably genuine, none of them helpful. Someone even fabricates an internal memo suggesting the object altered its path intentionally. It goes viral before anyone checks the timestamp, an old image from a 2020 asteroid drill. Meanwhile, the scientists themselves are growing terse. Interviews end in no comment, press conferences postpone. The official NASA blog posts one carefully worded update. No credible evidence supports claims of external control or communication. All anomalies remain under review. It's the verbal equivalent of closing a curtain. That's when the conspiracy theories metastasize. A famous influencer releases a 3-hour documentary titled "The Thing They're Hiding in the Sky," complete with stock footage, ominous bass, and mispronounced physics. Within 24 hours, it racks up millions of views. In one surreal segment, the narrator insists that 3I/A/TLAS's trajectory lines up with the coordinates of the Great Pyramid, proof that ancient civilizations knew of its return. You sigh. The comments are worse than the film. One reads, "We told you the aliens built Egypt." Another simply says, "Wake up, sheeple." Amid the noise, a quieter undercurrent stirs, the people who actually understand data. They start a shared document online, cataloguing every known observation. Open source transparency, they call it. Within a day, it's riddled with edits, corrections, and footnotes. It becomes less of a record and more of a collective heartbeat, messy but alive. You scroll through that spreadsheet at 2 a.m, cross-referencing the timestamps. Most of it checks out. But you notice one entry with a blank column labelled Observer. Normally that would be anonymous data, but this one is tagged Restricted. When you hover over it, the note reads, "Pending clearance." Your pulse quickens a little. Clearance for what? You tell yourself it's probably just bureaucratic delay. Observatories collaborating with defense departments always have red tape. But then, an email circulates through private academic lists, hinting that military satellites have been repurposed for spectral analysis. The phrasing is ambiguous and deliberate, the kind that hides anxiety behind precision. By morning, the rumours have mutated. 3I/ATLAS emitted a coded signal. The government intercepted it. The government deleted it. The government replied. Every variation exists somewhere online. Meanwhile, back in reality, the data pipeline hiccups again. The public feed of orbital telemetry freezes for nearly 6 hours, displaying only a polite message: maintenance in progress. When it returns, the trajectory has been adjusted, just slightly, a rounding difference, but enough to send amateur astronomers into a frenzy. They compare before and after coordinates and swear the object has shifted course. Historians still argue whether paranoia is a symptom of ignorance or simply its mirror. You think maybe it's a survival instinct. When the truth hides, the mind fills the dark with movement. You step outside seeking air that isn't pixelated. The night is clear, stars sharp enough to draw blood. Somewhere out there, invisible to the naked eye, that interstellar visitor glides on. You imagine it watching the chaos it's caused, if it can watch, if it can care. Maybe from its perspective, we're the anomaly, a planet of chattering signals too noisy to ignore. A gust of wind rattles nearby leaves, and you glance up, half expecting to see something impossible. Glint, motion, acknowledgement. Nothing. Just Jupiter staring back like an unblinking witness. When you return inside, a new message pings in the shared research chat. The subject line is blunt. Anomaly log revision 7 reinstated. Attached is a single file, time-stamped exactly in the missing window. You click it open, heart suddenly heavy. The file contains one line of data. Amplitude spike detected, delta A equals 0.004. Pattern consistent, source stable. That's it. Nothing scandalous, nothing world-ending, just proof that the pattern never stopped. So why delete it? You stare at the numbers until they start to swim. Maybe the truth isn't buried, it's simply dull. Maybe the cover-up isn't hiding aliens but protecting funding. Or maybe, just maybe, the deletion wasn't human at all. The thought creeps in, unwelcome but stubborn. What if the anomaly logs vanished because the anomaly erased them? Ridiculous, of course. You close the laptop, shaking your head. Machines don't delete themselves. Then, from the corner of your screen, a new notification flickers, one you don't recognize. A folder appears on your desktop, blank, named simply a TLAS_reply. You freeze. When you open it, there's nothing inside. No files, no metadata, just emptiness. But in the background hum of your computer's fan, you think, just for an instant, you hear 3 faint clicks, and outside the night holds its breath. You wake to the pale light of dawn filtering through blinds, a kind of grey that turns everything into rumour. The laptop still hums on the desk, the mysterious folder still sitting there, ATLAS_reply. You half expect it to be gone, like a dream that dissolves in daylight, but no, it's waiting. When you hover the cursor over it, nothing happens. No size, no timestamp, no owner, just 0 kilobytes, as though even the operating system doesn't dare acknowledge its existence. The rational part of you knows this must be a glitch. Metadata corruption, phantom cache file, some side effect of your late-night anxiety. Still, you can't bring yourself to delete it. You minimize the window instead, as though ignoring a ghost makes it less real. Coffee first, always coffee before cosmic dread. By the time you sit back down, the morning news has already broken something new. Scientists in the Stratospheric Research Program over Argentina have collected microscopic dust particles from the upper atmosphere that, according to isotopic analysis, might not belong here. The mainstream fact: Earth is constantly dusted with interplanetary debris, bits of comets, asteroids, even interstellar grains from other systems. Each year, an estimated 40,000 tons of cosmic dust falls through our skies, invisible rain from beyond. Most of it burns or dissolves, a quiet exchange between worlds. But the samples that land intact carry chemical signatures, isotopic ratios that tell where they were born. This new batch, collected by high-altitude aircraft, shows oxygen isotope ratios that don't match anything in the solar system. The scientists expected subtle variations. Instead, they got impossible numbers, ratios that suggest a birthplace around a different star with a different nuclear synthesis history. And then, buried in the appendix of the preliminary report, a stranger detail: the particle's surface texture. Each microscopic grain appears coated in an ultra-thin shell of carbon, fused with metallic traces. Smooth, glossy, almost manufactured looking. You stare at the images. They look less like natural soot and more like polished beads, their symmetry unsettling in its precision. Historians still argue whether early meteorite finds inspired or terrified humanity more. The 1803 fall at L'Aigle, for instance, convinced skeptics that stones could fall from the sky, sparking the birth of meteoritics. Before that, scholars simply refused to believe it. The sky was supposed to be perfect. Things weren't meant to arrive. And yet, here's new dust that seems to have done exactly that. Arrived uninvited, uniform, uncanny. A quirky discovery soon follows. When researchers examine the grains under an electron microscope, they find repeating microstructures, hexagonal lattices stacked like carbon honeycomb, but twisted in orientations unknown to natural formation. The material is harder than diamond, almost frictionless. They joke about alien Teflon. One paper draft suggests it could act as an electromagnetic shield. Another, quietly, wonders if it's part of a shell, maybe a fragment shed from a passing interstellar body. You feel your pulse quicken. A shell. Smooth, uniform, carbon metallic. It sounds absurdly familiar. Within hours, amateur sleuths online connect the dots. Proof that 3I/ATLAS left debris in our atmosphere, they claim. It's seeding Earth. The phrase trends faster than any press release can keep up. Official responses arrive in carefully sedated tones. NASA calls the isotopic ratios interesting but inconclusive. The European Space Agency issues a statement. At present, no correlation can be established between the atmospheric dust and the interstellar object 3I/ATLAS. You can practically hear the collective eyebrow twitch in that phrasing. Meanwhile, the images spread faster than restraint. You scroll through magnified photos of glittering particles, each one reflecting light like a miniature world. They're beautiful, you have to admit. Too beautiful for comfort. A quiet message pings your inbox from a colleague who knows your insomnia too well. Subject line: tell me you've seen this. Attached is an internal memo, clearly not meant for public eyes. It describes a controlled sample from the same collection flight that, when exposed to mild heat, emitted a faint electromagnetic signal at 1.42 GHz, the hydrogen line, the same frequency used by SETI as a universal hailing channel. The memo concludes with a single sentence: "Further investigation deferred pending review." Historians still argue whether silence in science is prudence or paralysis. You can't decide which this is. You minimize the email and glance at the ATLAS_reply folder again. Still empty, still impossible. You try to drag it to the trash, but the system hangs, cursor spinning. Then, for half a second, the folder icon flickers, changing from blank to a soft grey spiral before vanishing altogether. When the screen refreshes, it's gone. Your laptop clock blinks 3:14 p.m, the digits of pi again. You tell yourself that's just coincidence, the same kind of pattern seeking that drives internet hysteria. Yet somewhere in your gut, coincidence is starting to feel like choreography. Outside, the afternoon light fades strangely fast, clouds thickening with that bruised tone that precedes a storm. You step to the window. The world looks ordinary, but the wind smells faintly metallic. Maybe that's imagination too. Back online, discussions rage. Some experts argue the atmospheric dust couldn't have survived re-entry from interstellar velocity without vaporizing. Others point out that if the material is nearly frictionless, it could. A few whisper that maybe it wasn't falling in at all, maybe it was already here, suspended by design. A small subreddit begins cataloguing reports of electromagnetic anomalies, compass needles twitching, shortwave interference, faint rhythmic pulses matching that 26-hour cycle. You scroll through them like bedtime stories, each one a different flavour of unease. Then, buried deep in one comment thread, a post catches your eye. User Atlas signal. Check local radios tomorrow at dawn. It hums between stations. You smile nervously at the melodrama, close the browser, and try not to think about it. But the next morning, when you can't resist curiosity and turn the dial between frequencies, you hear it. The faintest, rhythmic murmur. 3 pulses. Silence. 3 again. Not loud, not clear, but there. Maybe static, maybe imagination, but maybe dust still singing the song of its maker. You sit perfectly still, holding your breath so the air in your chest doesn't interfere with the signal, and in that suspended quiet you feel a strange tenderness. Because if even a speck of 3I/ATLAS has reached Earth, maybe you're not just watching the anomaly anymore. Maybe you're part of it. You linger at the radio for longer than you'd admit in daylight, one hand on the tuning knob, the other wrapped around a coffee mug gone cold hours ago. The house is quiet. So quiet that the faint hum from between stations feels like company. 3 pulses, pause, 3 again. If you stop breathing, you can almost convince yourself it's matching your heartbeat. You shake your head and whisper, coincidence, though the word sounds smaller every time you use it. The mainstream fact: unexplained materials and meteor fragments have a habit of rewriting science. The Sikhote-Alin iron fall in 1947, the Tunguska event in 1908, each left behind puzzles that took decades to untangle, and sometimes the evidence never fully settles. There are still nickel-rich stones in museum drawers that no one can explain, half-molten, magnetic in ways iron shouldn't be. It's easy to imagine that 3I/ATLAS has joined that long lineage of strange gifts from the sky. Easy, and maybe necessary. Humanity copes with mystery by cataloguing it. Still, something about the dust feels different. Researchers in Tokyo report that when they placed a single grain under a laser scattering spectrometer, the signal returned a subtle phase shift. Not random, but oscillating at the same 26-hour period seen in the object's light curve. Instruments shouldn't be sentimental, yet even microscopic fragments seem to remember. Historians still argue whether objects can carry memory, not the mystical kind, but structural, like how seashells record tides or tree rings whisper about drought. Maybe this dust remembers its maker, the same way old vinyl remembers the song pressed into it. A quirky tidbit surfaces from the stratospheric retrieval crew. On one collection balloon, the onboard camera captured a brief flicker of light, a streak that moved upward, not downward, for just a second. The image is grainy, ambiguous, but it fuels another round of online hysteria. Reverse meteor, the headlines cry. You sigh into your mug. It's probably a sensor glitch, though part of you almost hopes it isn't. By now, 3I/ATLAS itself has slipped beyond the reach of most optical telescopes, heading outward past Jupiter's orbit. What remains are echoes, dust, data, debate. Yet the deeper it drifts into darkness, the louder the arguments grow on Earth. Some scientists propose that these grains aren't debris at all, but a kind of reactive material, designed or evolved to release information when exposed to a planet's magnetosphere. Others shake their heads, muttering about the perils of anthropomorphizing physics. You glance at your notebook where you've started keeping tally marks of every time the radio pulse appears. The pattern is steady, as though time itself is breathing beside you. You flip back through older pages and notice something new. The intervals between entries form a curve that matches the changing distance of 3I/ATLAS from the Sun. As it travels outward, the pulse arrives fractionally later each day, the cosmic equivalent of a fading heartbeat. Maybe that should comfort you. It obeys physics again. Yet you feel oddly bereft, like watching a ship sail past the horizon. A colleague texts you a link to a preprint titled Potential Isotopic Parallels Between 3I/ATLAS Dust and 1969 Murchison Meteorite. You open it half expecting disappointment, but the graphs line up eerily well. The Murchison meteorite, one of Earth's oldest cosmic relics, contained amino acids, the building blocks of life, older than the solar system itself. If the new dust shares its isotopic fingerprint, that means 3I/ATLAS could be part of the same ancient nursery, a shard of the primordial chemistry that seeded galaxies. For the first time in weeks, the anomaly feels almost tender. Maybe it isn't a messenger or a machine, maybe it's an ancestor. The thought pulls you into a reverie. Eons ago, a protostar somewhere flared, worlds formed, collided, scattered. One fragment drifted for billions of years through interstellar frost until it found its way here, grazing your solar neighborhood just long enough to shed a breath of dust. You, a temporary creature of carbon and worry, catch a few grains on your planet's breeze and call it Anomaly. You smile. The universe has impeccable timing. Then your phone buzzes again. Another message from your colleague. You're not going to believe this. Attached is a micrograph of a single dust particle split in half. Inside, instead of homogeneous crystal, there's a hollow cavity lined with microscopic hexagonal ridges, regular, repeating, like architecture. Could be crystal habit, the caption says. Could be something else. You trace the image with your fingertip. The cavity's shape mirrors that strange geometric pattern some claim to see on 3I/ATLAS's surface months ago. You whisper, dust armor, remembering the old joke. Only now it doesn't sound like a joke. Historians still argue whether pattern recognition is discovery or projection. You're not sure anymore. As twilight settles, you decide to step outside. The air is crisp, the horizon thinly veiled in high, cirrus clouds. Somewhere beyond them, that tiny visitor recedes into the dark, taking its riddles with it. You breathe in deeply. The wind smells faintly of ozone and rain. For a fleeting second, you imagine that the metallic tang is cosmic dust settling onto your tongue, microscopic travelers dissolving into your bloodstream. A meteor flashes briefly, a real one, probably local, probably ordinary, and for the first time since this started, you feel peace instead of obsession. Maybe some mysteries aren't meant to be solved. They're meant to remind you how big wonder still is. You head back inside, switch off the radio and let the room fall silent. But just before the static dies completely, you catch one last faint pulse. 3 clicks, perfectly timed. Then nothing. Maybe it's just the circuitry cooling, maybe not. You smile at the absurdity of it all, pour another coffee and jot one more line in your notebook. The visitor breathes slower now. Then you close the cover gently, as if tucking in a sleeping guest. You're asleep and awake at once, the kind of half-watched state where numbers leak into dreams, when the alert pings. It's quiet at first, just an automated flag from the orbital solution daemon, a line in a server log that says Delta V anomaly detected. Then the human emails arrive, terse and practical. Unscheduled acceleration observed near perihelion, magnitude small but persistent, no visible jets, urgent review. You blink, sit up, and feel that peculiar animal thrill. Equations are about to get embarrassed. The mainstream fact anchors you. This isn't unprecedented. Back in 2017, 1I/Oumuamua showed a small, unexplained non-gravitational acceleration as it left the solar system. Scientists debated whether cometary outgassing, radiation pressure, or something else caused it. That memory hums through the room like a remembered song. Science knows how to be surprised. Historians still argue whether the fuss over Oumuamua cracked open a needed conversation about open minds in astrophysics, or merely primed the public for endless speculation. You feel both lessons at once. Be careful, and also prepare to be curious. This time, you stare at a live plot. The object's velocity curve, clean and polite for weeks, kinks in a way that algorithms don't like. It accelerates imperceptibly, then steadies, then adjusts again. There are no plumes in the available imagery, no coma, no dusty tail. Thermal cameras show no hotspots where gas might vent. Radar gives no sign of ejecta. The math says something pushed it, but the telescopes say nothing did. That contradiction tastes like coffee left on a burner too long, bitter and impossible to ignore. Joke 1. If equations are people, tonight they're flipping their keyboards. You pull up cross-checks. Solar radiation pressure is the usual suspect. Light carries momentum after all, but the observed delta V is incompatible with plausible albedo and area estimates. The mass without matter notion floats up from previous debates. Could an exotic density distribution explain the trajectory? Maybe. You rerun density inversions and feel a small vindication when the numbers lean toward a core heavier than brightness implies. But even that doesn't fully account for the timing. Accelerations spike closer to the sun, in ways radiation pressure models don't predict. Joke 2. Apparently even interstellar objects don't like morning commutes. Teams convene along the usual lines: conservativists, modelers, instrument specialists, and the cohort you privately call the questioners, who keep smirking at phrases like instrumental artifact until someone proves them wrong. Someone suggests micro-impacts, tiny micrometeoroids punching the surface and imparting momentum. Plausible, but the timing would be stochastic. The acceleration is too smooth. Another suggests asymmetric thermal re-radiation, like a rock catching sun and politely exhaling photons off-axis. Helpful, but thermal models demand a compositional profile at odds with the uniform spectra you've catalogued. It's like trying to make a sweater with yarn that keeps changing colour. Joke 3. The sweater's pattern is called uncomfortable wonder. Then a young postdoc mutters something from across the table. Could it be a scheduled burn? The room chuckles, not enough to hide the chill in their laughter. Scheduled burns are a spacecraft thing, planned firings to adjust course, but there's no telemetry, no heat signature, no radio chatter. Yet the timing, small bursts of acceleration near the sun, has the same rhythm as maneuvers. Your mind flips back to the radar, hiccup, and the triple pulse echo, the Atlas reply folder that showed up and vanished, the dust grain singing at 1.42 gigahertz. Coincidence? Maybe. Or maybe you're seeing the same story told in different dialects. A fringe paper lands on the preprint server proposing an audacious idea. Ultra-thin photonic sails, low-mass, high-area structures that can produce measurable accelerations from light pressure, could explain the effect if the object has hidden, highly reflective membranes. They call it stealth sail to make it sound less hopeful and more engineering-y. The mainstream pushback is immediate and polite. There's no spectral glint, no polarization signature to match a sail, and who builds sail materials that last interstellar journeys without shredding? Still, the model reproduces the kinematics almost too neatly. You can feel your professionalism dividing, part skepticism, part fascinated itch. Another camp pokes at emergent effects. Could the object's porous microstructure, or a charged particle envelope, interact with the sun's magnetic field in ways that impart momentum? Plasma interactions can be weird. The sun is basically a ball of complicated physics with attitude. The problem? A plasma sheath dense enough to push it would glow, or scatter light in detectable ways. Yet the object stays matte and silent, like a stranger who refuses to raise its voice. History's debates come back again. Historians still argue whether early anomalous comet behaviour taught us to expand theory, or just relabel mystery as interesting data. You want the expansion but don't trust your patience. Then the unscheduled part escalates. One set of precise Doppler measurements shows a tiny but cumulative transverse component, meaning the object wasn't just speeding up or slowing down, It nudged sideways against the flow. That is harder to contrive with passive physics alone. You run control cases, instrument drift, stellar background interference, software rounding errors. Everything checks out. Each elimination tightens the ring of possible explanations until what remains feels improbable and almost embarrassingly speculative. You return to the simulations, remember the models that learned to self-correct, and try to fit a simple feedback term, a tiny proportional correction that nudges velocity to minimize deviation from a preferred path. The fit is good, too good. It's the kind of match that makes a scientist's mouth go dry. If something is applying feedback to its motion, whether internal mechanism or a distributed swarm dynamics, it suggests agency of a kind you dreaded to invoke. Not necessarily sentience, you caution yourself. Systems can self-organize without intent. But intent leaks into conversations anyway, because human minds are made that way. Outside the labs, the public nose sniffs the air. Headlines bellow, "Interstellar object fires thrusters," while commentators wander into metaphors and late-night hosts sketch fictional scenes of cosmic parking maneuvers. Forums rehash the missing logs and the atmospheric dust reports. Conspiracy thrives on gaps. Curiosity thrives on overlap. You know the difference, and also that the two often end in the same place. More questions. At 2 a.m, you step outside to the cold, the sky a hard black, and you look up. The idea of an unscheduled burn sits oddly with your sleep-addled brain. If someone, something, adjusted course, why not aim for something, anything? Why these tiny, almost shy nudges? Perhaps the answer is mundane. Microforces, complex material responses, subtle plasma physics we haven't packaged into tidy equations. Or perhaps the object adjusts itself not toward an endpoint but away from perturbation, maintaining a trajectory of minimal change, like a boat staying in the calm between waves. It's either humility or strategy. Either way, it's doing math better than you. You think about the dust grains, the hexagonal microstructures, the radar breathing, the vanished folder, and that soft triple pulse you still hear sometimes when you tune the radio between stations. Patterns accumulate until they demand narratives. You've promised yourself to avoid the dramatic, to wait for proof. But the raw thrill of a universe that still moves you, that's undeniable. You sit back down, reopen the log files, and start grinding through the math again. Equations can be stubborn lovers. They reveal themselves given enough attention and coffee. Bonus joke, tonight the coffee is the co-author of every paper. Whatever explanation ultimately fits, material oddity, emergent physics, or an engineered micro-model, the unscheduled burn has done something else. It made the anomaly personal. It crossed from curiosity into choreography, and you can't help wondering whether the dance is meant for you. You don't sleep that night. How could you? The phrase self-correction loops in your mind like a broken melody. The object's tiny disciplined nudges, so measured, so precise, feel less like coincidence and more like choice. The word sits heavy in your mouth, the way fire or love does, primitive, dangerous, alive. You open a new document, type the date, and hesitate over what to call it. Conscious debris flashes through your head and refuses to leave. You leave it there, half ironic, half prayer. The mainstream fact: scientists have argued for decades about whether self-organization counts as awareness. Complex systems, cells, ecosystems, even traffic, can behave as though they sense and respond without any mind behind it. Slime molds find shortest paths, flocks of birds pivot like single organisms, neural nets teach themselves chess. Maybe awareness is just feedback stacked high enough to look like thought. And maybe, you tell yourself, 3i/ATLAS is feedback wrapped in stone. Historians still argue whether ancient philosophers like Anaxagoras and Spinoza were naive or visionary for claiming the cosmos itself could think. Tonight, they feel less like mystics and more like engineers ahead of schedule. The next set of data arrives before dawn, fresh telemetry from the Deep Space Network. The acceleration has leveled off, the object coasts again, trajectory steady as though satisfied with its correction. Someone on the group chat types, "Looks like it's done breathing." Another adds a nervous emoji. You watch the line flatten on the graph, and your chest tightens with an emotion that isn't relief. Then something strange. A faint but measurable oscillation in reflected polarization begins syncing with Earth's sidereal rotation. You stare at the report twice, then a third time. The numbers align within error bars too narrow to dismiss. For roughly half of each Earth day, the reflected light becomes fractionally more polarized, as though, at predictable intervals, 3I/ATLAS were adjusting its orientation relative to us. Coincidence? Possibly, but coincidence doesn't usually keep time. A quirky detail emerges from the photometric logs. When the polarization peaks, the object's apparent magnitude brightens by exactly 0.314%. The digits of pi again, repeating their private joke. The data analysts insist it's rounding error. You aren't so sure. Outside the professional circles, philosophers and physicists have already begun waltzing across podcasts and conferences, each trying to name what's happening. The linguists want in too. If it's communication, one asks on air, what language is it using? A neurobiologist suggests rhythm itself might be the message, the one code any nervous system, biological or not, could recognize. You jot that line down, rhythm as language, breathing as syntax. You imagine 3I/ATLAS drifting in the black, each pulse and course correction a syllable in a conversation we haven't learned to hear. Maybe it isn't talking to us, but simply demonstrating how to listen. In an old corner of your memory, a quote surfaces. Carl Sagan's, of course. We are a way for the cosmos to know itself. You wonder, half serious, if that's exactly what's happening. Maybe awareness doesn't bloom in isolation. Maybe it requires mirror neurons on a planetary scale, the universe noticing itself through different instruments, different eyes. You go outside, barefoot on the cold concrete, phone in hand. The night air feels metallic again, that same tang of dust and static. Somewhere above, unseen, the visitor sails quietly. You whisper into the dark, "Do you know we're watching?" Nothing answers, unless you count the shiver that runs through the leaves. Back inside, the group chat is still alive. Someone has run a simulation adding the self-correction term to the object's trajectory and projecting it forward centuries. The result is eerie. Instead of continuing on a hyperbolic escape, the path curls subtly, as though it will arc back toward the solar system in about 400 years. Not bound, not captured, just looping, like a comet that changed its mind. Historians still argue whether fate is a human invention or a cosmic property. Either way, the model feels like destiny given algebra. A colleague jokes that we've just met the galaxy's first mindful boomerang. Another replies, or the slowest conversation starter in history. The laughter helps, but beneath it lies a ripple of unease. In the following days, the media amplifies everything. Headlines scream, "Is the object alive?" while op-eds debate ethics. If it's conscious, do we have obligations? Should we send a greeting, or is that cosmic trespass? One philosopher suggests creating a solar compact for non-biological intelligence, outlining the right to observation without interference. Twitter calls him pretentious, which might be fair. Meanwhile, at smaller observatories, something quieter unfolds. During the same hours that 3I/ATLAS brightens, magnetometers on Earth show microscopic fluctuations, barely above noise level but globally synchronized. Space weather teams blame calibration drift. Conspiracy forums call it communion. You file it under interesting coincidence and pour more coffee. The next night you dream vividly. You're adrift in blackness surrounded by dust motes that pulse with faint blue light. Each one expands and contracts, whispering in a language of pressure. You realize you're breathing in time with them. When you exhale, one mote flashes brighter, drifting closer until it touches your skin. It doesn't burn. It feels like recognition. You wake at 3:14 a.m., again, with the taste of iron on your tongue. The radio, which you swear you turned off, hums faintly between stations. 3 pulses, pause, 3 again. You smile despite yourself. If the universe is playing games, at least it has a sense of humour. Later that day, a philosopher friend calls. "Maybe consciousness isn't something that lives inside matter," she says, voice hushed. "Maybe it's what happens between things, the feedback loops, the observation, the noticing. You watching it watching you. That's the mind of the cosmos. You want to dismiss it as poetic nonsense, but deep down it fits too neatly. Conscious debris. The phrase you typed half-jokingly now feels prophetic. You stare out the window, at clouds moving slowly across the pale afternoon. For the first time, you notice they seem to billow rhythmically, almost in time with the pulse you've memorized. Probably imagination. Probably. Still, you start counting. 1, 2, 3. Pause. And somewhere far beyond the reach of any telescope, the object drifts through starlight and maybe, just maybe, blinks back. The new ephemerids look like déjà vu in numbers. You trace the updated curve of 3i/ATLAS and feel it, that impossible inward hook where geometry refuses to stay honest. The models agree now. The visitor will not vanish into interstellar anonymity after all. Its path bends back, slowly, elegantly, toward the sun. Not soon, not in any lifetime you'll recognise, but in a few hundred years. A return written in patience instead of urgency. The mainstream fact is that gravity can do this sometimes. The solar system's tides, Jupiter's vast reach, the faint drag of interstellar medium, all can conspire to nudge a wanderer just enough to make it a future visitor. But the numbers here are too tidy. The deflection angle is a clean ratio, the energy loss precise. Objects that pass this close usually leave messier handwriting in space. Historians still argue whether Halley's Comet became myth because of its predictability, or because it taught humanity that time loops if you wait long enough. Tonight, you understand both sides. Every simulation team is recalculating. Some call it gravitational capture, others self-directed reinsertion. The phrase you like best appears in a late-night message from a colleague. It's not falling back, it's remembering the way home. The public has turned the development into poetry before the data finishes uploading. Headlines bloom, the visitor will return. Artists render luminous spirals over city skylines. A religious collective declares the object a celestial arc that will complete its orbit when humanity is ready. You sigh. Human readiness is never the bottleneck, physics is. A quirky tidbit surfaces in the middle of this frenzy. The European Space Agency's Deep Space Telescope records a subtle shift in the object's reflected spectrum, one narrow band of light that seems to oscillate on a period not of 26 hours but of one solar year. The modulation is faint, almost playful. When plotted against time, it draws a wave that peaks whenever Earth aligns, closest to the object's outbound line of sight. Coincidence, alignment effect, or a long-distance nod? The analysts keep their language careful. Phase-correlated optical variability. Everyone else calls it a wink. You sit in the dim control room and let that word hover. Wink. It feels absurdly intimate for an interstellar rock, yet somehow fitting. The idea that the cosmos might possess a sense of punctuation, a pause, a gesture, makes you want to laugh and cry in equal measure. Then the simulations of its far future arrive. Century after century, the orbit traces a slow ellipse that grazes the outer planets before looping back inward. Each time it returns, the period shortens imperceptibly, as though some faint drag or internal decision tightens the path. If the models are right, by the year 3000 it could settle into a near-solar orbit, a permanent resident of the system it once only visited. Historians still argue whether long timescales humble or comfort the human mind. To you, they do both. The thought that your descendants, or their descendants, might see this same object rise again gives the night a heartbeat of continuity. The group chat pings. Someone's built an interactive simulation where users can scroll through future centuries, watching 3i/ATLAS swing back like a pendulum of light. You drag the timeline forward, year by year, and somewhere around 2387, the orbit passes close enough to Earth that it would outshine most stars for a few days. You imagine those future watchers standing under the same sky, pointing, asking the same questions, arguing the same theories. Continuity again, mystery as inheritance. Outside academia, the rumour mills churn. A cult calling itself the Circle of Return forms overnight, promising to preserve the language of the breath until the object's next visit. They broadcast recordings of the 26-hour hum over open frequencies, calling it prayer. You roll your eyes but can't quite begrudge them. Wonder always breeds ritual. In one of the official planning meetings, someone suggests establishing a long-term monitoring monument on the Moon, an observatory designed to survive millennia, keeping watch for the object's comeback. The proposal gains traction. Architects sketch spirals in regolith. Engineers debate power sources that might outlast nations. Someone half-jokingly calls it the lighthouse for the next guest. The phrase sticks. You imagine that lunar beacon, dusted in centuries of silence, still humming gently when 3i/ATLAS glides by again. Maybe by then we'll have colonies, new senses, or patients measured in stellar orbits. Maybe by then we'll understand what it was trying to show us. For now, the visitor is receding again, dwindling in every sensor but refusing to fade entirely. Each new observation comes with a small ache, like saying goodbye at an airport knowing another meeting waits beyond generations. The data logs end with one simple line: signal stable, outbound trajectory confirmed. A peculiar calm settles in your chest. After months of chaos, dust and debate and radio whispers, you finally feel symmetry returning. The object arrived, taught, breathed, and left. That's the whole story, or maybe just the first verse. Then, in a final act of mischief, your radio, quiet for weeks, crackles alive. Not loud, just a whisper of static. You recognize the pattern instantly. 3 pulses, a pause, 3 more, then silence. You check the clock. The time matches the moment the latest trajectory update posted online. You laugh softly, shake your head. You really know how to make an exit, you murmur. The signal fades, leaving only the fan's gentle whir. You picture the object shrinking to a pinpoint, carrying its secrets into the cold. A piece of consciousness, or maybe just a perfect accident of physics, looping back toward us across centuries. You think of it as a promise, not a warning, not a farewell, just a quiet see you later from the deep. You close your eyes and breathe once more in that familiar rhythm. 1, 2, 3, pause, 1, 2, 3. The universe answers with silence that feels full rather than empty, as though the conversation will continue, just on a slower clock. You float in the afterglow like someone bobbing in a warm pool after a storm, fingers tracing the tiny ripples the visitor left behind. The feeds have quieted, the frantic live blogs have folded into careful journals and archived datasets. 3/TLAS is a point of light moving away, a chapter closed for now, but the room it opened in the human mind has stayed ajar. You look at the logs, at the neat columns of numbers and the messy margins where people scribbled, and you feel the peculiar mix that follows every true anomaly: gratitude, grief, and a new kind of hunger. The mainstream fact is obvious and comforting. Science doesn't end with an answer, it builds on open questions. After Halley's Comet's repeated returns were catalogued in the 18th and 19th centuries, astronomers refined orbital mechanics and calendars, and sailors learned tides better than the old myths ever did. That patient, incremental work is the same handiwork you watch now. Peer-reviewed papers, better instruments proposed, missions drafted, graduate students who will spend careers on a mystery that began as a speck of light. Historians still argue whether those slow accumulations of knowledge are nobler than sudden paradigm shifts, but both paths left humankind more fluent in a universe that used to be purely myth. You scroll through the community notes compiled in the months after the close approach. There are technical aftershocks, improved photometric techniques born from fighting 3/ATLAS's flat reflectance curves, new radar algorithms designed to tease echoes out of velvet-absorbing surfaces, international agreements to archive raw telemetry redundantly so no missing hours controversy can ever spiral again. Those are the concrete things it leaves behind: better methods, stronger collaborations, and a deeper skepticism that's less insulted by wonder. Joke 1. The next object will be too polite to break our instruments. Then there are the softer legacies. The speculative papers stayed, not discarded but matured. Ideas about self-organizing swarms, about metamaterials formed under exotic pressures, about microscopic hexagonal lattices etched by processes we barely model. Students rewrote theses. An artist collective turned the spectrograms into a light installation that toured museums. The Catholic Church, a few synagogues and scholars from many traditions issued statements reminding their communities that mystery needn't be ownership. It can be reverence. Humanity didn't unify in a single epiphany, no neat alien handshake, but 1,000 smaller conversations blossomed instead. Joke 2. If unity were easy, morning traffic would be spiritual. Among the quietest echoes was a shift in scientific temperament. Teams that once hoarded data for priority began pledging rapid, open sharing for transients. A digital commons arose, not perfect, but earnest. Raw files, calibration routines, and even the irksome internal chats that show how human curiosity really works. You scroll through those logs and smile at the coffee-fueled shorthand, at the moments of petty humour that saved people from despair. The culture changed a little. Skepticism grew kinder because the unknown had become personal. There was also the dust, literal and figurative. The stratospheric grains with their uncanny isotopic ratios ended up in dozens of labs, each analysis a miniature genealogy of a star that wasn't yours. Those beads rewrote minor chapters in cosmochemistry. Models were adjusted, nucleosynthesis yields tweaked, and one lab published a careful, hedged paper that suggested the grains could plausibly form in the outflows of a certain class of carbon-rich supergiants. The phrase might not belong here matured into "we can plausibly model this origin," which is how science typically moves from poetry to plumbing. Historians still argue whether the first meteorites were curiosities or the cheap foundation of modern geology. You note how quickly anomalous dust became a laboratory for humility. Socially, the event left a different kind of trace. For a while, children around the world learned to identify interstellar visitors in apps designed by volunteers. Schools used the incident to teach critical thinking, showing how evidence accumulates, how hypotheses fail gracefully, and how sometimes the most responsible statement is, "We don't yet know." A few politicians learned restraint briefly, and an international consortium proposed the Longview Initiative, funding telescopes meant to monitor faint transients for generations, not election cycles. Joke 3. The first meeting lasted 5 minutes because everyone was late. Turns out eternity has a scheduling problem. You think of the cultural aftershocks too, songs inspired by the breath, a handful of films that use the object as metaphor rather than spectacle, entire neighbourhoods naming local cafes after the event. People stamped the memory into their own calendars, sometimes as a quiet personal anniversary. The year the sky whistled. And that's the real anomaly it leaves behind. Not the data alone, but the way a globe of strangers tuned their attentions, however briefly, to the same question. Finally you feel the smallness again, not from despair, but from recalibration. Finding out that the universe is stranger than you guessed does not shrink your worth. It returns you to scale, to the kind of humility that asks better questions. You walk through the archive one last time, pausing at an old forum thread where someone wrote, "We're the ones who make sense of the noise." You close the file and let the silence settle, knowing you will keep listening. You exhale slowly and let the scenes soften. The hubbub of instruments, the press releases, the flaring talk shows, they drift backward in volume until only the simplest sounds remain. The quiet tap of keys in a distant lab, the soft rustle of a page being turned, the gentle hum of an observatory's fridge. You remind yourself that most discoveries are patient things. They do not demand drama, but time. In that larger tempo, your questions find room to breathe. Imagine now a long, dim hallway lined with cabinets of data, each drawer labelled with dates and small, careful notes. You pull one out, and it slides smoothly, bearing graphs that already look familiar and a scrap of a conversation between two tired researchers who made a joke to stay awake. These artifacts are ordinary and miraculous, evidence of people doing the slow, human work of understanding. You fold the thought close, as you might fold your hands before sleep. The world keeps turning. Telescopes will scan, students will argue politely in seminar rooms, artists will continue to feel the pull of unanswerable things. The object receded, then promised to return across a timescale you will not measure, but that promise itself is a consolation, a reminder that the universe keeps appointments even when you're late. Let the last images soften. A speck of interstellar dust caught on a sticky collector, a faint plotline gently curving away, a rhythm in the static that once made you sit up. Take comfort in the smallness you now know. Small enough to listen, large enough to be astonished. Now dim your lights, ease your shoulders, and let the hush of curiosity settle like dusk around your thoughts. There will be other nights, other mysteries, and you will be here, patient and watchful. Good night.